Omkar, एक minute, just a minute, ma'am. Omkar sir joined us.
Okay.
Hello, Omkar sir. हाँ sir, you joined us. Okay. Good. आपका support is required. बस अभी मैं वही सोच रही हूँ. I committed with speaker की 12:25 पर join कर लेंगी. तो उसके बाद 12:25 पर जब भी वो ज्वाइन करती है फिर प्रिंसिपल ज्वाइन करते हैं, देन वी विल स्टार्ट ग्रीन सिग्नल फॉर स्ट्रीमिंग. नाउ वी आर स्टार्ट. बस अभी वेट करती हूँ 4 मिनट 3 मिनट हो गए.
बस अपन लोग ही है ना इसके अंदर, कितने लोग हैं ना.
now we can start on YouTube streaming.
Omkar sir, give me an indication when should I start? Okay. Good afternoon to one and all. I, Assistant Professor Sheena Unmesh, on behalf of Excelsior Education Society's KC College of Engineering, Management Studies and Research, Thane, consider it a great honor to welcome our eminent guests, speakers, delegates, participants, and all my dear staff members to the International Seminar on Emerging Technologies of Nanosciences, Environment and Energy, COVID-19 Restriction, hosted by Department of Humanities and Applied Sciences in association with IQAC and Institute Innovation Council. We would like to thank our Honorable Chairperson, Dr. Harsh Khanna, Managing Director, Dr. Sai Kiran Khanna, Chief Operating Officer, Dr. Pooja Rai Pradhan, for giving us this privilege to organize the seminar. Before we proceed with the seminar, I would like to take this opportunity to thank all the participants from all over India and abroad for their overwhelming response to take part in this event during this lockdown and make it a huge success with more than 1,000 participants. Thank you all very much. This seminar focuses on three integral and significant parts of today's life, that is science, environment, and energy. So here we are with this two-day seminar to help you to get the perfect insight from all our eminent speakers of various fields and virtues. Now, may I have the pleasure of requesting our principal of KC College of Engineering, Management Studies and Research, Thane, Dr. Vilas Nitnavre, to please share some few words and inaugurate the seminar. I request sir to please take over the mic. Thank you so much.
Thank you, Professor Sheena. Am I audible enough?
Yes, sir, you're audible.
Okay. Good morning to you all. I, Dr. Vilas Nitnavre, Principal of KC College of Engineering and Management Studies and Research at Thane, welcome you all in today's international seminar on emerging technologies in nanoscience, environment, and energy. Our Honorable Chairperson, Dr. Harsh Khanna, have broader vision, in which she wished that the campus should be vibrant, round the clock, with activities, whether online or offline. Situation should not dictate the terms, but we should mold the situation as per our convenience. I am glad to know that Dr. Shaili, along with her team members, came forward to organize the event this time. Getting all the Tare Jamin Par, I mean to say that getting international speakers from different countries on one platform is really a matter of proud for all of us. It indicates her meticulous planning and rigorous follow-up. So I take this an opportunity to congratulate to the organizers, and I wish that this trend of organizing great event will continue in the future too in KC campus. Somewhere I read that we don't grow when things are easy, we grow when we face challenges. Challenges exhaust us, but its fruit is never ending when we reach to milestone. I'm glad to see that the same spirit is being continued by both the participants as well as resource person, that the trend of learning is continued even in challenging circumstances like COVID-19. Dear friends, you can teach a student a lesson for a day, but if you can teach him learning by creating curiosity, he will continue the learning process as long as he lives. I mean to say that if you as a teacher is curious to unfold the mystery, I am confident that the students will follow the footsteps of their mentors. I am also glad to know that all the topics proposed in this seminar are mostly research in the field of material science, life science, and energy. Somewhere I read that research is a discovery of truth, particularly as far as the natural sciences are concerned. Iteration is one of the keys to successful research, but research should be outcome based. Researchers usually do not end. The studies goes on deep and deep, but researchers should definitely know that their research should address the problem of human being, society, and industry at large. There is no use of such research if it is simply getting recorded in some research papers and books and articles. Sometimes it may be good, as it may become the reference to new researchers. But the real thrill and satisfaction lies when we see the efforts of our research is being used for the welfare of the society and globe at large. I request the resource person of today's seminar to keep open the area of COVID-19 for the participant. Let the thinking process of participants to go on. As I came to know that there are thousands of participants enrolled for this program, so thinking process of thousands of mind will start at the same time. We cannot predict which mind will bring the effective technological solutions to get rid of the intensity of this COVID-19, which made the entire world paralyzed. In today's world, everything changes very rapidly and continuously. The education institute should produce a graduate to cope up with the technological development and ensures that the graduates will have knowledge, skills, attitude, and behavior to work with any competent area. I would like to tell you one thing very prominently here is that not only the students of engineering college should know the difficulty due to existing problem, but it should be brought into notice of all the students of other stream too. This will help the undergraduates to find out the effective solution by the time he completes his studies, and probably his solution will be visible by his last year project too. Dear friends, I am truly obliged to all the participants that they enroll in large number in this 2 days international seminar conducted by KC College of Engineering. So I take this privilege to tell in short the vision of my organization. The ultimate aim of our management and staff is to prepare our students to think global and act local for purposeful placement in multinational companies. We at KC College of Engineering continuously strives to produce competent technocrats and managers who will make significant contribution to the corporate world and industries all over the world. As a result of our efforts, many of our past students are now leaders in their profession at various industries such as Microsoft, Reliance, TCS, Infosys, Amazon, and many more. The program has become the international due to acceptance of our eminent resource persons from all over the globe. I convey my sincerest thanks to all of them because of whom the program has become the reality. So to be started with, I would like to convey my sincerest thanks to Professor Sunita Ratan, Dean Faculty of Science and Technology, Director, AIAS, Amity, University Noida, Dr. Andras Sapi, Faculty in University of Zegel, Hungary, Mr. Sinoj Bhaskar, Director in Production Management, Aspen Tech, Houston, Texas, United States of America, Professor Deepa Khushlani, Department of Chemical Sciences, TIFR, Dr. Pradeep Kumar Roy, Faculty in Department of Ceramic Engineering, IIT, DHU, Dr. Tunde Alapi, Faculty in University of Szeged, Hungary, Dr. Seema Garg, Associate Professor, Department of Chemistry, Amity Institute of Applied Science, Noida. I convey my sincerest thanks to all the speakers once again, and I'm confident that the resource person will handle the session in a more effective way and will create the impact of the topic in their mind so that those topics will be further converted as a research topic and research will lead to product. With this, I convey my best wishes to the resource person as well as participants. Thank you so much. Over to Professor Sina.
Thank you, sir. Your words of encouragement means a lot to us, sir. Thank you so much. Let us begin the session without any delay, and it's a great honor to welcome Dr. Sunita Ratan, Professor and Director, MIT Institute of Applied Sciences, MIT University, Uttar Pradesh, Noida. She has held many administrative and academic positions throughout her career. She has a rich experience of 25 years in academics and research. Her research area includes polymer grafting, ion beam modification, stimulus-responsive polymeric membranes, sensors, nanomaterials, and nanocomposite. She has published more than 50 research papers in reputed national and international journals and presented around 70 papers in conferences. She has given more than 12 invited talks at various international conferences, and she has filed 14 patents, out of which 2 granted and 3 are in pipeline at the final stage of being awarded. She has edited a number of books and has contributed chapters in the books with publishers like Royal Society of Chemistry, Springer, and Nova Publishers. Her books written for engineering students are popular among students and also included in the list of books provided by the AICTE. She has funded projects from reputed funding organizations including DRDO, DSTU, IUAC, BRNS, SERP, and 2 from the international agencies such as Inter-Atomic Energy Association, Austria. Professor Sunita Ratan has supervised a number of students for their PhD programs. She has international research collaborations. In addition to above assignments, she is serving as a secretary to Asian Polymer Association and Society for Biomaterials and Artificial Organs, Delhi. Ma'am, may I request you to start the session on homogeneous dispersion of nanomaterials in polymer matrices. Welcome, madam. Welcome to the session. Over to Professor Sunita Ratan.
Thank you, Professor Sheena. It was a nice introduction. I would like to share my slides first before I start with my topic today. So just give me a moment so that I can share. Is it visible to all? My screen is visible? Hello?
Yes, ma'am.
It is visible.
Yes.
Yeah, my PPT is visible to all?
Yes, sir. Yes, sir.
Yeah. So a very good afternoon. First of all, I would like to thank all the organizers for giving me a chance to present my research over here. It is a wonderful opportunity, and COVID-19 lockdown has given us this advantage of sitting at home, talking to each other, interacting with one another, so that we can go for more collaborations and think for the solutions of the global challenges what we have got. My today's topic is homogeneous dispersion of nanoparticles within the polymer matrices, a new approach. So I start with my presentation, but before I start with my presentation, I would like to give you a glimpse of our Amity Education Group, that is Amity University. Just 5 minutes. Amity Education Group has got 8 universities, 150 plus institutions, 18 schools and preschools, 11 international campuses, 125,000 students, 10,000 faculty and scientists, 1,000 acres of campuses, over 5 million square feet of high-tech buildings, 250 programs covering more than 60 disciplines, 300 high-tech science and technology labs, 80 linkages with universities globally, 25,000 scholarship awarded till now, and 27,000 on-campus placement in the last 5 years. I've just give you a glimpse of some of the important campuses. This is our Delhi campus, or you can say NCR campus. It is situated in Noida, and it is the biggest one, or you can say that is the mother of all the campuses. This is the another campus which is very near to the NCR or Noida campus, that is the greater Noida campus. This is our campus in Lucknow, which is very much gel with the architectural sites of the Lucknow. This is our Jaipur campus, pollution-free campus. This is our Manesar campus, Haryana. This is in Haryana. Our aim is to actually open a campus in every state. And this is very near to you. That is Mumbai campus. This is our Gwalior campus, which is very much like the, you can see, Havelis of the Rajas, which they used to have. This is Kolkata campus, very much with the architecture of the Calcutta, merged with the architecture of Calcutta. This is our Raipur campus, this is the Ranchi campus, Patna campus. And then it's not that we've got the campuses in India. We have got the campuses outside also, because Amity wants to spread its wings to the global scenario also. So you've got Amity Singapore, Mauritius, New York, Dubai, and it's not that we are in higher education, we are into the school educations as well. So we've got number of CBSE school in India and abroad. So these are some of the schools overseas. You can say we've got Abu Dhabi, then Dubai, Sharjah, Singapore, South Africa, Amsterdam, and then Dubai again. And it is back, Amity University is backed by 6,000 distinguished faculty who are totally devoted to the research. We have filed 1,040 patents, authored 500 books, published around 7,000 papers, 2,400 case studies, and some of the leading institutions and government organizations from where Amity faculty have drawn is actually starts from DRDU to AIMS to agriculture to earth sciences to DST. We have got a number of distinguished fellows in Amity University to guide us, mentor our path, mentor the young faculty to achieve the greater heights. And these are the number of programs, you name it and we have it. Because we are a very progressive university. We do not only are confined to the conventional programs. We go for very different programs as well. And this is my Amity Institute of Applied Sciences, where I am the director. We've got 4 departments, physics, chemistry, maths, and stats, and we run MSc and BSc courses. As this is an engineering courses, let me also add that our faculty also takes care of all the engineering branches in Amity University, be it electronics, computer science, civil, etc. So it is our faculty who go and teach them. So we are very, very synchronized with you, because we are teaching the BTech students as well, along with the BSc and MSc programs. Now, I come to my topic. When we say composite, what exactly do I mean by composite? Composite consists of 2 or more chemically distinct material, which when combined have improved properties over the individual materials. That's a very simple definition or scientific definition. But when we say composite, we say one is the matrix phase and another is the dispersed phase. So when both of these combine, we say that is a composite. But now out of the 2 things, which one would we call the matrix and which one we would call the dispersed? The one which is the continuous phase, and the other one where you have to put little amount of that is actually known as the dispersed phase. I'll elaborate it further in my next slide. If you can see, I am in today's lecture, I will be confining my talk to polymer nanocomposite. So polymer is the continuous phase. So I can say polymer is the metric here, and whatever I include in that polymer, that is actually the you can say the another phase. You can say inclusion is that's a composite. When we polymer matrix, and you can say dispersed phase, when we mix these 2, we get the polymer composite. But when we say polymer nanocomposite, from the word nano, what exactly we understand? Nano means that one of the phases, either it should be the matrix or the dispersed phase, that should have the nano dimension. So now having matrix as a nano dimension is a difficult thing, though people are working on it. But in here, I am concentrating towards the dispersed phase, which is in the nano size, right? So these are some of the figures. You can see that this is the matrix, or you can say that some of the figures you can see that this is the matrix, or you can say this is the dispersed phase. Right? So now when I say why polymer nanocomposites, because when we say polymers, they are around the world. People say ban plastic, but I want to ask them that how we can ban the plastic. It has gone in so deep into our existence that we can only talk for biodegradable plastics. We cannot ban the polymers. Right? If you can think, you're sitting, just see how many things you're wearing. And I will bet it that each one of you will see at least 20 things are made up of plastics, right? For you, right? Your frame, your specs, your buttons, your watch, your computers where you're working on. So we have to do what we have to actually do. We cannot ban the plastic. We have to come with the innovative ways where we can have better tailor-made plastic for different use, for specific use. And then next session is that we can have biodegradable plastics. So now, why do we need to improve the polymer properties? Why do we need to improve the properties, and what nanocomposite do to the polymer? It actually causes unexpected improvement in properties like mechanical properties, electrical conductivity, flame retardancy, improved appearance, chemical resistance, thermal stability. So why we are talking of polymer as a matrix? Because matrix can be a metal, matrix can be a ceramic. Why we are only concentrating on polymer? Because polymer give me the leverage of tailor making any substance. You name it and I can actually tune the properties as per the requirement, because they are lightweight, they are corrosion resistant, their exceptional processability, easy fabrication, durability, and relatively low cost. So these are some of the advantages which make polymer as the desirous material as a matrix. Now, when we say polymer nano composite, again I'm coming to that, the filler. Now, if the filler, what we can do, we can say we can take a polymer as an insulating polymer, or we can go for the conducting. The polymer is insulating polymer, and filler we can take conducting. Now, see what great property enhancement has occurred. You know, we use plastic that it doesn't conduct electricity, but in today's world, in electronics, we require, in computer science, we require the plastics for making the conduction. We require them for semiconducting materials. So what we can do, we can take the insulating polymer and we add a conducting nanofiller, and the result is semiconducting material. Right? Now, this semiconducting material is very different from the semiconducting materials which we have been using. Why it is so different? Because now we have the semiconducting material which is tunable, which is robust, which is flexible, which is durable, which is not the case with the conventional semiconductor materials. Right? So that is the advantages. Applications of polymer nanocomposites, we have got electronics, which have already have discussed. Aeronauticals, we are having polymer nanocomposites. Solar panels, we are having polymer nanocomposites. Conductive inks, duracells, actuators, and biosensor. This is one of the very important field where we are having polymer nanocomposites for sensing applications. Right? So that was the advantage. But it's not that easy as well, because when I say that I want to mix the polymer with the conducting nanofiller, it can be a simple mixing which will not actually yield the results which we want, right? So the challenge is that the dominating factor, because I'm telling you that polymer, and if I put the filler in that, it will have a different property. But from where that different property comes? From where the dominating factor in the development of nanocomposite and realizing the properties of the nanocomposite is the interface between the matrix and the filler, which the present world is actually not talking much. We are taking the polymer, we are mixing the, you can say, we are taking the polymer, mixing the nanofiller, and we are forming something and we say it has got a different property. No, that is actually not required. What is giving the new properties to the nanocomposite? It is the interface. The interface controls the degree of interaction between the filler and the matrix. And that is what controls the property. That is what enhances the property. Right? So properties of nanoparticles cannot be fully realized in polymer nanocomposites if there is a poor dispersion or poor interfacial interaction between the particle which is being filled into the polymer and the polymer matrix. Thus, the main challenge in preparing polymer nanocomposites is to disperse nanoparticles well in polymer matrices and improve polymer nanoparticle interfacial interaction. I'll just show you. Here you will get to know. When I say this is the polymer matrix, and let's say these are the nanoparticles which are dispersed. If I say matrix, if I only characterize this part, do you think that this part will have different properties than the polymer? No, because it's simple polymer. If I go and characterize this part, nanoparticle, would it have different property? No, it will have the property of nanofiller. So what is new? Why am I mixing these two? What am I getting? What I am getting, if you go to this figure, you see where the polymer and the nanoparticles, their boundary is actually giving me new properties. This is the interface I am talking of. This is the interface which will actually give me a new material. Now, this is the material which is neither a polymer nor the nanoparticle, but it is a new material with new properties, improved properties. So that's why there is a simple book which is written on this, polymer nanocomposite interfaces. Actually, that is the hidden lever for optimizing performance in nanofilled polymers. So I think I am able to tell you about the importance of the interface. When we need to go for nanocomposite preparation, we have to talk in terms of that we have to increase the density of the interfaces. We have to increase the number of interfaces, because interface is the new material actually. So interfacial region, the length scale is reduced from micrometers to nanometers. So the role of interface becomes crucial, because here this is the phase dominated, this is one phase, this is another phase. So phase dominated properties, they become the interface dominated properties. That is what is actually required in polymer nanocomposites. So therefore, interface can have altered chemistry, altered polymer chain mobility, altered degree of cure, and altered crystallinity. And it can be as small as 2 nanometer, or it can be as large as about 50 nanometers. So that is our actually expertise, our skill, how we play with the interface to give us the good properties, right? So now, various methods so far to assess the dispersion of the filler. You must have been seeing a number of papers where if I have to prepare the nanocomposite, how do I prepare? I just take the polymer, I take the nanofiller, mix it, form the film, and I say it's a new material. No, those are the conventional, though some important property enhancement comes, but it is not at that scale which the world is looking for. It is not at that scale which the specific applications are looking for. So, to implement novel properties of the nanocomposite, processing methods that lead to control, particle size distribution, dispersion, and interfacial interactions are critical. So effective processing technique, this is what I was telling you. Either we go for in situ polymerization, or we just melt processes. We melt the polymer along with the nanofillers, and we can get the polymer nanocomposite. We go for ultrasonic mixing. We go for molding. So these are the conventional processing technique, but there are drawbacks, because there is poor interfacial interaction, lack of uniform dispersion. One side will be having high properties, another side will be having low properties, because there is no uniform dispersion, low efficiency, incompetent to control the reaction condition, less control on molecular weight of the polymer, lack of control on reaction conditions. So therefore, our objective was to synthesize the polymer nanocomposites using different processing techniques for the preparation of novel polymer nanocomposite films, which introduce a high density of interfaces in composite system. Or next, to demonstrate that the strategies employed produce the PNCs, polymer nanocomposites, I mean to say, with significant increase in flexibility, mechanical strength, durability, electrical, and thermal properties. And then, what application we will be looking for? We were looking for chemical vapor sensors and structural materials for aerospace. So we have been preparing these polymer nanocomposites for these two applications, though they can be evaluated for other applications as well. Right, so we've taken 2 polymer matrices. One, we've taken polystyrene, which is a thermoplastic polymers. I hope the viewers know what are the thermoplastic polymers. And another one, we are using the conducting polymers, that is P dot, polyethylene dioxythiophene. Right, so we have taken one insulating polymer and one conducting polymer. Right, so what is the filler we are actually interested? I think everyone would be knowing that carbon has actually been worked on by a number of researchers because of its very good properties, right? In carbon-based fillers, we've got graphite, carbon powder, carbon fiber, carbon nanotube, fullerene, and nanographite platelets. So this is actually why I have marked it in red, because nanographite platelets is what we will be working on. What exactly is nanographite platelets? Nanographite platelets consist of small stacks of graphene, right? I think you know what is graphite. Graphite is a layered structure. So one layer is actually graphene, right? But it is very difficult to get one layer. Graphene is actually difficult to get. So instead of getting graphene, or we just wanted it to be cost effective, so getting graphene is not cost effective. We wanted cost effectiveness with all the properties which graphene has. So we went for nano graphite platelets, right? So if graphene is one atom thick planar sheet of sp2 bonded carbon atoms, NGPs, they are 2 or 3 atoms thick, right? But fortunately, their cost is so low compared to that of graphene, but their properties are remarkable properties just like graphene. So that was the reason why we chose nanographite platelets. Therefore, a substantial research is still necessary to introduce a novel processing route which can provide strong interfacial interaction along with the complete exfoliation of the NGPs within the polymer matrix. Why? Because when we want to disperse the nanographite into the polymer, the chains do not separate because they are actually having van der Waals forces among them. So the main challenge is that these should be separated, right? And they should be dispersed uniformly because they have got the property to get agglomerate. Once they get agglomerate in the polymer matrix, we will not have the property. So we wanted to take care of this challenge, and we started with some approaches. One approach was use of swift heavy ions, which I will be discussing. Another is click reaction. Another is grafting of polymer matrix on filler. And another is thioene reaction between matrix and the filler. But I will be concentrating my talk on the first two, click reaction. Let me tell you, it's not only polymer matrix, you can use anywhere. If you want to synthesize something through green chemistry, click reaction is the one which you should go for. Click reaction is the one which actually happens in the aqueous phase. What exactly is click chemistry? What is click chemistry? It is a concept introduced by Barry Sharpless in 2001, which describes chemistry tailored to generate substances quickly. When I say click, right, we use this phrase click. So this is what we want to say, that I have two substances, I want them to react quickly, I say click, right? But once we want to react these two substances quickly, we should have a complementary groups. For example, I say here it is the azide group, here it is the alkyne group, right? If I take a component having azide group, another group having the alkyne group, and I click it, immediately it will form a triazole. Within no time, no reaction, no very specific reaction conditions. So that is click, right? So we got the idea from here, and we say when we are taking a polymer and the nanofiller, why don't we functionalize them with these azide and alkyne group? Once we do that, and when we mix, there will be proper covalent bond formation. So with this idea, this is a patented idea. We've been awarded the patent for this. What we did, we went for the same idea. This is what I was telling you, that it is not that advantages of click chemistry is only in the nanocomposite. You can go for various other uses also. So what we did, first we took NGPs, right? Nanographite platelets. Graphite, as you know, you can see that this is a graphite, right? This is actually, if you go microscopically, you can see it is a layered structure. What we want to say, graphite flakes we put in the beaker. This is a Hummer's method, very important method. And if you are working on graphite, you must be knowing about this method. So these are the graphite flakes. Our main aim is that we want that these graphite flakes should be exfoliated like this. They should be spread like this. So what we did, we took the graphite flakes, first through acids, they were intercalated, and then through the process, they were exfoliated, means these stacks were actually exfoliated, right? And they filtered and they were dried. So that was the first we prepared the NGPs. Now, this is very interesting if you would pay some attention, that this is NGPs. As I've discussed the click reaction, what we did, we just took the NGPs and introduced the alkyne reaction over here. right? We just functionalize them with the compounds. In this case, it is para-aminophenyl propyrogyl ether, that it actually introduces these alkyne linkages over there. So our one component is ready with the alkyne linkage. We took the polystyrene, that is the polymer, which is the next one, and we functionalize it with the azide. This is what, if you, again, I go back to this slide, and I'll tell you that this is the azide group, this is the alkyne group. So these are the two components. In my case, this is the polymer, this is the nanographite, and I have introduced these two components in here. This is alkyne, this is the azide. Now that these two reaction becomes very easy. Compare it with the mixing. When we were mixing, there were no functional groups, and mixing was giving me very rough heterogeneous mixture. Now, once I mix these two through the click reaction, this is the alkyne azide functionalized, this is the alkyne functionalized. When I mix these two, I get nano composites, which is a triazole conjugated. And let me tell you, friends, that has given us enormous enhancement in the properties, right? So this is a pictorial representation of the whole process, and you will see how beautifully this has been explained, that this is, you can say, NGPs. You can see NGPs are so light. When we functionalize it with alkyne, they go here. And if you want to disperse the NGPs in water, they are not soluble. You disperse the polymer in water, it is not soluble. But once you prepare the nanocomposite by the method which I have discussed, you see the nanocomposite is so much soluble, proper homogeneous solution is there. So that is actually the beauty of functionalizing and then interacting the functionalized group to prepare the nanocomposites. These are the FTIR studies which exactly show that this azide group has already entered into the combination with the alkyne group, because in this composite we do not see any azide group because it has already reacted to form the triazoles. So this is the same peak which is actually shown here, enhanced manner, that this is the CNC's composite nanocomposite where there is no azide peak. This means azide has entered into a combination. These are the nuclear magnetic resonance spectroscopy. We corroborated our results with nuclear magnetic spectroscopy to see that whether the component has been found, the azide-alkyne linkages has taken place. So without going into the details, I would like to say that these graphs show, yes, very nicely, it has gone into that click reaction. Again, the NGPs show a typical sharp diffraction peak at 24.1 and with a D-spacing. D-spacing, again, I will like to tell you that exfoliation, right? Exfoliation means the distance between the two layers of the graphene is 0.37, right? And when we alkynate it, when we enter the functional group, alkyne functional group to it, the exfoliation increases to 0.54. What does this mean? 0.37 to 0.54 means what? That the exfoliation has taken place, the layers are now separated, right? So now, when they are separated, again, when we put the polymer in here, the D-spacing reduced to 0.44, but that is acceptable because the D-spacing of NGP is 0.34 and in polymer nanocomposite, it becomes to 0.34, and that was very much understandable because when you are putting the second component is bridging the two layers together. So bridge, due to that bridge, the loss of exfoliation is there, but that is actually desirable, right? So you can see the thermogravimetric analysis. NGPs, the loss started below 100 degrees centigrade. The thermal loss started below 100 degrees centigrade, and then it becomes to decompose and then degrade. Whereas polystyrene, if you can say separately, again it also degrades. But when we say CNCs, you can see there is no loss till 340 degrees centigrade. And when it goes at a higher temperature, there is again a residue. And this residue is actually due to the formation of those triazole groups, which I have discussed earlier. And you can see beautiful SEM images of the graphite nanoplatelets, flakes like graphite nanoplatelets. You compare it with the figure I show you, which was just looking like a coal, right? And you can see the figure which is showing you beautiful flakes. Right, so these are the TEM images from where we can see these layers, and these layers can be counted, that what exactly is the exfoliation distance between, or the despacing between the layers, right? And what is the application? We used it for hydrogen peroxide sensor, right? Why it is necessary to actually sense the hydrogen peroxide? Because they are being used as crude explosive devices for terrorist activities. Terrorists are using the hydrogen peroxide, right? So we need to actually sense it, whether in the container contains hydrogen peroxide, whether the vapors are there around, right? So due to the highly toxic nature of hydrogen peroxide vapors and use in explosive devices, it needs to be monitored with reliability to safeguard the health of workers in hazardous industries. Because wherever people are working with hydrogen peroxide, again, it is not very good, it's toxic. So sensing of hydrogen peroxide is very imminent. So we have actually gone to prepare the chemical sensor with this nanocomposite. What exactly do I mean by chemical sensor? Because it is a measurement device that converts a chemical or a physical property of a specific analyte into a measurable signal. Right? Means that what exactly is the property change, and that is measured. Like that chemical or the sensor should actually sense it and produce a change in the property. Right? For example, sometimes the light glows, right? There are a number of sensing mechanisms. But here we are using the sensing mechanism that your resistance or your conductance changes. Once your nanocomposite comes in contact with the hydrogen peroxide sensor, there is a change in the conductance, or there is a change in the resistance. So once that change is there and it is measurable, you get to know that in the room there are hydrogen peroxide vapors. Right? But requirement for good chemical senses are fast response, high sensitivity, high reliability, transform chemical quantities to electrical signal, maintain their activity over a long period of time, and it should be small, cheap, specific, and low detection limit. For example, if I say I want to go to the airport with a bag, I want to check the baggage, and if I got a huge equipment with me, no, it won't work, right? And that is very cumbersome. So I need a handheld device, just handheld device, which can sense just like a torch. So we have, these are the results. You can see that very beautifully. You can see that for hydrogen peroxide vapors, if there is no, if you can see this graph, can you see my mouse? So this is the graph where you can see that this is air, right? Air means the resistance is around 10 raised to power 8 ohms. But the moment hydrogen peroxide, it sends the hydrogen peroxide, the resistance drops. So there is 3 orders of resistance drops. So this can actually be linked to a glower or linked to some voltage, which can give you the, which can sense it, which can give you the sensitivity. Right? So you can say the resistance of CNCs before exposure to hydrogen peroxide vapor was measured at 1.08 into 10 raised to 8 ohms, and it just decreased to 1.29 into 10 raised to 6. 10 raised to 8 to 10 raised to 6 is a huge difference in the resistance. So that's a very, very good sensor for hydrogen peroxide vapor sensing. And beauty of this is, it's not that you sense it and you throw it away. No, it is fast response. But within 3 seconds, it will tell you that hydrogen peroxide is there. And if you want to repeat it, if you want to use it again, you just expose it into the air. It will come back. The resistance will come back to its original value. And it can be repeatedly used. You can see from this graph that how repeatedly it can be used. This is in air, then again to hydrogen peroxide, then in air. So we have done this experiment, and it has got beautiful reproducibility and the resistance. So highlights is the judicial selection of click reaction has improved polymer filler dispersion. Why we could get 10 raised to power 3 orders, 10 raised to power 3 change in resistivity? Because there was property enhancement at the molecular level, at the nano level. Interfaces were high. So the resistance of CNC is, I've already discussed this. So it is a promising sensor material which gives a spontaneous response within 3 seconds of exposure to hydrogen peroxide vapors with complete recovery at room temperature by just exposing the sensor to the air. Have you ever heard of a sensor which can be just recovered by exposing it to a sensor? This is it. The prepared CNC gas sensor has the potential to be used in fabrication of an efficient, portable, handheld device. This is actually I wanted to emphasize for hydrogen peroxide sensing at the low cost. So this was one of the examples of click chemistry. So we have been doing others also that we have also discussed the same. But here, sometimes it so happens that when we go, we want to fabricate the material, but mechanical properties are not there in the sample. So what do? So this work we actually did to increase the mechanical properties. So our focus was here that, okay, we have got the properties, we can utilize these materials as the sensors, but what about the mechanical strength? So we took the PMMA. PMMA is polymethyl methacrylate, which is a thermoplastic polymer, which is actually very good, robust, have many very good mechanical properties. So the same thing we did, I'm not repeating it because the same thing, we functionalized the polymer with azide group, we functionalized it with the alkyne group, we clicked these two and we got the composites. These are the composites which we got. And again, the characterization was very similar, which dispersion studies. And here also azide group was disappeared. This FTIR showed us, yes, these are being formed. And then these are the functionalization studies which we have discussed. So these are the NMR, which has actually led us to see our experiments are successful or not. And these are again the sum of the the NGPs. And these are the alkyne functionalized nanocomposites. And this is the polymer, which is PMMA. And when we combine these, this is the polymer nanocomposites nanographite. This is the composite. This is actually very strong, mechanically strong composite, which is polymer nanocomposites having very good mechanical stability. So these are again the same thing. You can say that TEM images where you can say the layered structure, and we can see the in the layered structure you can see how much is the despacing between these two. These are the beautiful flakes. Let me tell you, if you have got a flaky NGPs, they have got beautiful properties. They can impart so many properties to the polymers that you can explore them. So these are the TEM images. And these are the AFM images. The pristine NGP does not show any individually dispersed feature with average height of 15 to 20 nanometer and height profile of 200 nanometer, whereas PNCs have decreased the thickness of the layered sheets within the range of 2 to 5 nanometer, which is actually due to the exfoliation of NGPs, because NGPs has gone within the matrix, right? So now these are, you can see the mechanical properties, how they have increased. Pure PMA shows an elastic modulus of 3.3, whereas PNCs, polymer nanocomposites, 6.2. Can you see it's an increase of 87.8%? So you can see, as I discussed initially, that there is a change in the electrical properties. In my previous work, I have discussed the change in the electrical properties. Here I am telling you the change in the mechanical properties. 87.8% stronger. Right? Similarly, if you come to the hardness of PNCs, PMMA itself is very, very hard, right? Having the value of 0.17 GPa. But if you can see that when the polymer, it is actually graphite platelets are added by the method which we have discussed, there is an increase of 123.5% in the hardness. So you can see how the mechanical properties, there's a drastic increase in the mechanical properties, right? So these are possible mechanisms. Why it's so much change? Because properties, you can say nanographite is very fragile. You can say polymer, okay, it had the very strong properties. Why there is an increase? The increase because of that click reaction. I told you, triazoles are being formed due to the linking of the alkyne and the azide groups. And you can see these are the real pictures. I'm telling you that you can twist it, you can roll it, you can bend it. So when you have to make the device, you don't have to see कि अरे टूट जाएगा. No. You can fit in the device anywhere, any type you form. So that was the possible mechanism. But here, because hydrogen peroxide was already done, so here we used it for ammonia sensor. Now the drawback of ammonia is that it is very toxic with a pungent odor, and in high concentrations it can be flammable. So the people working out there are actually very much this thing, and before they get to, because ammonia has got a very pungent smell also, so you can smell it like this. Why we need a sensor? Because we can smell it, right? But before that happens, that they smell it, huge leaks are already done, and there are pressure drops in the valves. Right, so the leakage from the valve may decrease the efficiency of the refrigeration plant before it can be detected by the commercially available sensors, which work at room temperature only. So there is an urgent need for a sensor which can detect ammonia at low temperatures, because when you are using it the refrigeration plant, you are working with a low temperature. By the time you actually get that pungent smell, and that too at the room temperature, huge losses are already occurred, right? And some health hazards also there. So therefore, when we use this for ammonia gas, you can again see this graph, right? Now, this graph also tells you that when you are exposing it to the ammonia, the change in resistance is again within 2 seconds you can get it. Within 2 seconds you can get that, okay, ammonia is there, and that too at a very low concentrations, right? 2 orders, 4.46 into 10 raised to the power 4 to, it goes to 9.01 into 10 raised to the power 6 on exposure to ammonia. So that was the application, which is related to the mechanical strong, you can say strong polymers, right? So these are the highlights: highly flexible and mechanical strong films. Triazole linkages actually are related to the mechanical strong behavior, remarkable electrical, mechanical, and sensing properties. And one more thing, it is so beautifully properties are enhanced that our sensor not only works at room temperature, because if you can see 90% of the sensors, they work at very high temperatures. Only few literature reports are there which work at a lower temperature, at room temperature. But our sensor is working at 0 degrees centigrade as well. So that is the beauty of our sensor. So that was the 2 examples I had given you about the click chemistry, the nanocomposites, which were prepared by the novel approach using click chemistry. But then there is another very beautiful approach, which is swift heavy ions. This is also our patented work. Now, what exactly are swift heavy ions? Ion beams with high energy ranging from few tens of milli-electron volt to giga-electron volt of different elements. So when they pass through the polymers, you can see these are the polymer film. When these ions, they pass through the polymers, they pass through the polymer, they create these damaged zones. Can you see these are the damaged zone? Now, if you put this polymer into an acid, these damaged zone will give you the tracks, right? You will get very beautiful tracks over here. Right, so these are the swift heavy ions. So, but there are number of reports on material modifications using sheaths. Can I ask the organizers how much time is left so I can rearrange the talk according to that? Hello?
Ma'am, you can take 10 minutes more.
Right. So I'll just write. Okay. So material modification using swift heavy ions is already there.
Excuse me,
Yes.
ma'am.
Yes.
You can take 5 minutes to presentation, then 5 minutes we will keep for question answer sessions.
Okay. I'll try to do that. Thank you, ma'am. Thank you. So, She ions can be used to bring about modification in nanocomposites in 2 ways. Either the ion passes through the polymer matrix or ion is implanted inside the polymer matrix. So what we did, I'm just using it, that we have gone for polyethylene dioxythiophene PSS. This is a conducting polymer. And we wanted, first we prepared the film by solution blending technique. What do I mean by this? We took the solution of the polymer, we took the nanographite, we just stir it and we form the film. As I told you, this film is not homogeneous. This film may not have the interfaces which we are looking for. This film may have the agglomerates. So what we did, we irradiated with nickel ion beam. Now, when we irradiated with nickel ion beam, means nickel ion beam went inside the polymer and it left the polymer from the other side, polymer nanocomposite from the other side. But just passing of this nickel ion beam from the polymer, what it does? It has actually exfoliated the polymer. Can you see that? If this is the polymer and these are the simple films which are prepared by the solution blending technique, you can see how inhomogeneous are there. This is the polymer. We just put the NCs. NCs are poorly dispersed. They are agglomerated. We will not get the interface. The density of interfaces is not there, right? So what we did, we just took these films and we irradiated it. And now you can see. Can you see the difference? The agglomerated nanocomposites, which were of no use, though they had some use, but not that enhanced properties. And once we pass through the stiff heavy ions, these nanocomposites, you see beautifully arranged nanographite platelets within the polymer matrix, as if we have prepared them in mechanically sitting in the lab. Just this is what I wanted to tell you, the beauty of stiff heavy ions. Homogeneously dispersed. Now you can see your properties are very similar at 1 centimeter square centimeter or 1 millimeter or 1 nanometer or or you can say at any molecular level, right? So this was the method I used, and this is again the SEM images of the nanographites which are there. And these are some more images, well dispersed nanographite platelets with similar size. You can see it's not that size is also similar. Of the platelet size is also similar. So that gives more important properties to the polymer, right? And when we checked it, to know that when we checked it for the nitrobenzene sensitivity, again we used it for sensor application only, and we checked the sensitivity with nitrobenzene. And you will be surprised to know that before irradiation, it was 18.5% sensitivity. And after irradiation, it doubled. It just doubled. Right? So these are the patents which are actually we have filed according to this. What has the ion beam done? Ion beam ne kya? Because that mechanism is important to understand. For example, these are the nanographites. These are the polymer. Now, nanographite, what it does, in polymer nanographite composite, they are dispersed in the polymer matrix. Swift heavy ions creates a cylindrical molten zone, right? As you can see, it's a kitchen chemistry. You can say that when we actually try to dissolve anything in the thick liquid, it won't. But slightly just put the gas on, the viscosity will decrease and the thing will be mixed properly. It is not actually the same analogy, but you can see that this ion beam will create a molten zone of a few nanometers for a few seconds. And that molten zone will let the polymer get into the exfoliated space. So once it gets into the exfoliated space, this will no longer will remain a separate entity. It will be polymer nanocomposite in these entities. So that is the explanation. And you can see that sensor properties. This is what I have discussed. For irradiation, it was 16.5. Now it is 38.3. Similarly, we have done PMMA also, that was P dot. Similarly, we have done PMMA. So for the paucity of time, I will not go into this. But again, already given us very good sensor properties. And this I'm leaving carbon ion implantation. I don't think I have time. So thank you very much. Some other time I'll discuss these results also, because these are very important ones. So you can say I'll just go. This is the my group. These are my students. They are working. I've got two groups, nanocomposite group. I'm also working on a very important group, important work, that is hydrogel for biomedical properties. We are actually going for targeted drug delivery for cancer target areas, etc. So this is another group, and this is the group which is working on the nanocomposites. And these are acknowledgement. These are my collaborators from other universities. Thank you so much. Now the session is open for questions if you got any. Thank you for your patience listening. Thank you. Yes, over to the organizers.
Yes, ma'am. We are just checking if questions are coming to us, so we will forward to you. So I am waiting. There is one question, ma'am. What is the
Yeah.
difference between nano and mono
Yes.
crystalline? What is the
Mono.
difference? What is the difference between nano and monocrystalline?
Very good. See, when we say nano, nano is when we reduce something to 10 raised to power minus 9 nanometers, right? 10 raised to power minus 10 raised to power minus 9 meters means it is the size effect, right? Monocrystalline, that you are using one crystal, right? Here I'm not talking of numbers. Nano means I'm talking of the size. And you will be surprised to know, because I think this is a question from a student. If you go and see the nano world, when we say nano material, you take bulk material and you convert it into a nano material. The properties will be entirely different. You keep on, because it is a new science which says that if you have a mass, if you have got a bulk material, you keep on converting into smaller to smaller size, and when it goes to the nano range, the properties, the quantum mechanics exactly changes. The properties are totally new. There is a quantum confinement, and you can go to the YouTube and you see the gold, which is yellow in color. Once you go to nano size, see how beautifully it changes the color. And that is one example. There are so many. The whatever, for example, you can take the substances which are not very good at their bulk scale, but you take them to their nano levels, enormous change in the properties are there. So nano is actually related to the size. We are talking, when we take nano, we are talking of the size. And nano, as you can say, it's a very measurable 10 raised to 9 meters. So that,
Ma'am,
yes.
okay, ma'am, there is one more question. Why sol gel method is feasible?
Why sol gel method is?
Feasible.
It is actually feasible because sol gel method is actually the solution. People have been trying, the physicists have been trying to prepare the nanomaterials for number of methods, but sol gel method actually gives you the easiness of doing the experiments in the lab. Also, it is cost effective also. So these are some of the advantages of sol gel method, so that number of nanomaterials are actually being done by the sol gel methods, because they are easy, and their, you can say, production is very easy. The industrial macro scale production is very easy.
One more question, ma'am. Parameters which decides the interface properties.
Yeah. The parameters which decide the interface properties are the homogeneous dispersion. If your material is not dispersed, so therefore you'll have less number of interfaces, right? The density of the interfaces will be less, because interfaces, we are talking of the boundaries between the nanoparticle and the matrix. And if the boundaries are less, or you can say agglomerations are there, and the boundaries will be less, so your new material which we are talking of, which is being formed within the nano composite, is less. If that is less, the concentration of that is less, so therefore the enhancement in the properties is also less. So it is actually the more is the homogeneous dispersion, more is the exfoliation, 100% more will be the enhancement in the properties, more will be the interfacial regions. Right?
Thank you. Sheena ma'am, now we can conclude this session and then we will start another session. Dr. Indra Sapai is also with us. Sheena ma'am. Hello, Sheena ma'am.
Hello. Can I now unshare my slides? How do I unshare, ma'am?
Ma'am, click on stop sharing.
Okay. I don't see a stop sharing anywhere.
Okay. Omkar Nurgane sir. Omkar sir.
Okay, present 9. Okay. Thank you. Thank you
Okay.
so much. Thank you to the organizers to give me this chance to present my work. Thank you. Yeah, Dr. Andra Sapi, good morning. I would like to hear you also. Oh, thank you so much. How are you, sir?
Hi, Sunita. Yeah, thank you very much for your talk. It's good to see you. Yeah, hope to see you soon, in personal. Yeah, it was
That's
good to
good, sir. That's
hear
good.
your, yeah. Thank you very much. Yeah.
Okay, sir.
Hello, everybody.
Hello, sir.
Hello.
Sheena ma'am,
So,
please start. Sheena ma'am. Sheena ma'am.
We cannot hear you, Professor Sheena. I think there is something wrong with your voice.
Okay, okay. Sheena ma'am. I'm just checking. I'm just checking with her. Sheena ma'am. Hello. Sheena ma'am. Sheena ma'am, you are not audible, Sheena ma'am. Okay. So, okay, so Sheena ma'am, I am starting. Okay, Sapai sir, Omkar sir, hello. So should I start? So I can, okay. It is with great pleasure that I introduce the guest of the day. It is with great pleasure that I introduce the guest of the day, Dr. Indra Sapai from Hungary. Dr. Indra Sapai is chemist, Faculty of Chemistry, English Hungarian, professional interpreter. He is fluent with English language, French. In 2014, he completed postdoc from University of Berkeley, California, USA, currently pursuing faculty in University of Hungary. He has published 70 papers in IST Web of Science Citation Index 50. Cumulative impact factor is about 170. Citations without self-citation is 600. H index is 14. He also authored 2 books, 2 patents, 20 posters. These are all going to their credit. He has given about more than 50 oral presentations. He has also given many lectures and seminars on synthesis and application of nanomaterials in English, as well as in nanotechnology and material study laboratory, chemical industrial procedures and machines, chemical technology laboratory, environmental technology laboratory, environmental technical procedures and machines. He supervised 40 theses and various projects. He is also supervisor of BSc and MSc, Chemical Engineering, Environmental Sciences, BSc and MSc, Environmental Engineering of BSc and MSc, and Materials Sciences. He has several awards of his credit. Sir authored many projects, he guided many projects like industrial gas treatment based on zeolite, nanostructure, and platinum nanoparticles in 2007, 7, and 9. He also collaborated with University of Oulu. He has many patents. So that is a very small introduction about Sir, but he has done a lot of work, as I know, in the field of chemistry. So I, on the behalf of KCC MSR, my college.
Thank you. Okay, so thank you very much. Let me start my presentation just to be sure that everybody sees it. Okay, can you see the presentation?
Yes, sir.
Yes, sir.
Okay, that's great. So I'm gonna go to the presentation so I can see it clearly. Okay, you see my mouse is moving on the presentation. That's also okay.
Yes, sir. Your mouse is moving.
Okay, that's great. So first of all, I want to thank you for the organization. I know that it's a lot of work to put together an organization like this, and I really appreciate it. I'm really sorry about the virus which is happening in the world, but I'm also grateful, for these new possibilities to have, get together from all over the world, and then I'm grateful you putting together this seminar and this. So thank you very much, professors. I'm really grateful I can be here, and then let me start my presentation. So I also try to speak about, as Professor Sunita spoke about, a lot about interfaces, and then I'm going to speak about interfaces in a bit different manner, but also that's my belief too, that the interface is the key role in the field of heterogeneous catalysis also. So today I want to talk about catalysis, heterogeneous catalytic reactions, and then how can we use nanoparticles in these systems, and how can we designing these systems. And also I will show you what we do, how to try to understand these systems in a molecular level. And then from the molecular level understanding, how we can design our next. And at the end of the presentation, I will show you that this is not just a basic research. We love basic research, but also we can use it, and then we try to use it with industrial partners and to have nice applications about this heterogeneous catalytic measurements. So let me go through. So this is the group. Maybe this is not a brand new picture, but you can see the number of the people. So we are the Applied and Environmental Chemistry of the Department of Applied and Environmental Chemistry of the Faculty of Sciences at University of Szeged. And then this is Professor Konya. He's the head of the department, and also he's the vice rector now for the university. And then this is Professor Akos Kukovets. And then I can tell you a couple of students. This is Dori, this is Marcy, this is Kopri, this is Lotzi. They helped us a lot in this work, what I will show you also now. So just for introduction, we all know the Fischer-Tropsch synthesis. If you are chemists, we know that for the carbon gasification, we can get the syngas. And then from the syngas, at higher pressures, we can easily make fuels for our automobile. And then these people, so Fischer and Tropsch, they used a lot of catalysts, and then they tried more than 1,000 catalysts. When they find that, okay, the best one is the iron and cobalt system for this method. And then nowadays, also in the industry and also in the lab, we use this trial and error method. What we are doing is that we try, okay, we had 0.1 sodium, 0.2 sodium, 0.5 sodium, and so on. So this is what we do. Then we do a scale up, and then we do a lot of parametric designing before we go to the industrial usage, and which makes a lot of work. And also the other stuff which is happening in industry, that of course we are using nanoparticles. So this is what you can see here is a transmission electron microscopic images of alumina-based catalyst, which is supporting platinum nanoparticles on the surface. And then you can see in industrial catalyst, the sizes of the particles are different. So you can see particles which is 1-2 nanometer big, and you can see particles which are bigger, like 10 or 20 nanometer big. So the size effect, the real size effect is missing from here. And then, so what we try to do is that doing a catalysis by designing, using nanotechnology to avoid this huge amount of trial and error method. I mean, that is our plan. And also, I will speak a bit about how to designing interfaces, and then how can we improve with these designed interfaces the heterogeneous catalytic processes. And then also, as I told you, I will speak about the molecular level understanding, about in situ techniques. How can we check our reactions under molecular level under reaction conditions? So you know, so why nanostructures are good in heterogeneous catalysis. So in catalytic reactions, you have to know that everything is happening on the surface. So we need more surface. So if you see, here's a big nanopart. I'm sorry, somebody's microphone is on. And would you be so kind just to switch it off, please? Okay, thank you. So what you can see here, you see here a big nanoparticle, you know, which has almost 4,000 atoms inside. And then we chop it into 8 smaller cubes. You will still have the same amount of atoms, but on the surface you will see that almost twice as much atoms are on the surface. And then if we go down to a smaller level, so now we have a 4 by 4 cubes of nanoparticles. This is about a 1 nanometer nanoparticle. You can see that almost 90% of the atoms are on the surface. So you use the same amount of platinum, but your atoms are on the surface, which is active in catalytic reactions. So the surface to volume ratio is better, and then also there are more kinks and edges. And then in heterogeneous catalysis, it's not just the pure surfaces, but the kinks and edges are playing an important role. And then the numbers of them are really high in the nanoparticles. And also the cell parameter can be different, the surface charge can be different, and the surface rearrangement can be different in the nano level, which makes these nanoparticles are suitable candidates for heterogeneous catalytic reactions. I can tell you another example. So this is just single crystal studies. So this is a hexagonal platinum surface. It's a platinum 111 surface. This is 100. The only difference what you can see is that there are rows of platinum atoms. And in the platinum 111, you can see that the one row of the atoms are half atom shifted away. So this is a more structured, more compact structure compared to this one. You can say, okay, so what? This is almost the same. But no, just look at these reactions. The hexagonal surface can be twice or thrice more active in a reforming reaction compared to the square surface. Okay, so if you have different Miller indices surfaces, you will have different catalytic activity. Just think about it. So this is the basic reaction. The most basic reaction what I can show you is the adsorption of hydrogen over platinum 111 surface. This is how it looks like. The hydrogen molecule doesn't like to stay together, so it will be adsorbing or chemisorbing in an atomic level. And then you can see there are hydrogen atoms on the surfaces. This can be on the top side of a platinum atom. It can be on a bridge side. It can be on a 3/4 side. This can be on a 3/4 side pit side. And then this has, you can imagine, this has different energetics. These needs different energetics. And also, these atoms are not staying here. They are moving all over the surface every time. And then you need activation energy. So this guy can jump here, then jump there, then moving here. And this needs different energetics. So you can imagine if I bring here, for example, a benzene or a CO molecule, it can be different. So, and if you have different surfaces, you can imagine that you will have different energetics, which will lead to different activity and selectivity and heterogeneous catalysis. And just think about, you have, for example, a square type or a sphere type nanoparticle. It's never a sphere. So, but it has different Miller indexes surfaces with different concentrations. And if you have different sizes or different shapes, the concentration on the surface of these different faces will be different. So that's how you can change, you can tune the catalytic activity. Okay, so if you the message from here is that if you have different size and shape, you will have different Miller indices, which will give different surface chemical processes. And also not just the nanoparticles, but interfaces are can be in a really big action. So here are 3 examples. I will just show maybe this one. I think this was a really nice study. I really love this. So what these guys did is that, so they took a silica surface and they took a platinum nanoparticles and then ceria nanoparticles. So they make a sandwich with a Langmuir blow jet technique. So they added platinum nanoparticles on the surface, then they added ceria nanoparticles on the surface. Then they did it vice versa. So they had a platinum ceria silica sandwich and the ceria platina silica sandwich. And what they find in a hydroformylation reaction, this sandwich didn't work. However, the ceria platina silica sandwich worked. What happened? So they knew that this interface really played a crucial role in this reaction. So the ceria platina interface was an active interface for the methanol decomposition, and the platina silica was important for the hydroformylation reaction. Okay. And also about the in situ techniques, we use a diffuse reflectance IR spectroscopy. So we want to understand the reaction on the molecular level. And then, a lot of techniques, what you can do, you check your catalyst, you put it in the microscope, but there is a vacuum. So usually these particles are not stable. Under reaction conditions, atoms are jumping out to the surface, and then, the whole structure can be different, what you can see in vacuum or ex situ method than under reaction condition. And then we have a couple of tools to really understand what's going on in the reaction. This is the IR technique, and then also the some frequency generation. This is kind of an IR technique, which is really helpful in this reaction. And then also there is the ambient pressure XPS measurements, which can be really helpful. This is a UV ultra high vacuum technique. However, we can solve that under reaction condition. We do XPS technique. And then this example shows really nicely. So this was a palladium rhodium nanoparticle, core shell nanoparticle, where rhodium was on the surface and palladium was inside. However, if you add nitrogenous oxide and carbon monoxide together on the surface, the whole structure changed. So all the platinum is coming to the surface and then rhodium going inside into the nanoparticles. So these structures are changing. And then these are good tools to understand them under reaction condition. So now here is the, now I'm moving to how we did the synthesis of metallic or oxide nanoparticles. So you look, this is pretty easy. So everybody can do it. We just use this so-called the Schlenk reactor. You have to, we usually use the polyol method for this. You need metal salt precursors, which is dissolving in polyols, and then you need capping agents. Sometimes we use PVP. It's like soap, different soap. So it's kind of, I can say it's easy like, cooking a good curry or something, but also it's never gonna be the same. So you have to really get rid of water and then air, because that can influence the sizes. But with some techniques, you can, with experience, you can make really nice nanoparticles easily. So these are what we can do. So we can do platinum nanoparticles easily controlled. We have 2, 5, 7, 8, 12 nanometer particles. So you see, here are the size distribution of them. And so we can control the size in 1 or 2 nanometer regime easily. Also, we can do the same, for example, with copper nanoparticles. You can see nanoparticles here. Also, we did some cobalt and platinum cobalt alloy nanoparticles. You see, these are all 8 nanometer platinum nanoparticles, more or less, or 8 to 10 nanometers. And these are with the ratio of 1 to 3 or 1 to 2, 1 to 1. Platinum cobalt, alloy nanoparticles. So anyway, you can do whatever you want to do. And also the other side is the support. So in heterogeneous catalysis, you use a support, and then we use the so-called soft template and hard template method to make high surface area inorganic supports for our catalyst. And then I think this was really, this is showing nicely how we can do transient metal oxide with high surface area. So you make a skeleton of a mesoporous silica. then you add your metal salts, for example, nickel nitrate, cobalt nitrate, iron nitrate, and then you do a calcination, you get rid of the nitrate, so the oxide will remain there. And then after with sodium hydroxide, you can remove the silica, so you will have a replica of the mesoporous silica system, and you will have a mesoporous oxide. Here are two images of the different silicas and alumina, titanate, what we used, and also here are this hard template method: nickel oxide, ceria, cobalt oxide, manganese oxide. You know what's good in these guys is that what you buy in the shop, for example, from cobalt oxide, the surface area, which is really important in catalytic reaction, is about 10, 20, or 50 square meter per gram. However, for these materials, it can go up to 150 or 200. And the final synthesis of the catalyst is that you have the support, you have your catalyst, the nanoparticle, you use sonication, and then the nanoparticles will go on the surface, or if they are enough small, they can go into the pores. And then after, we have to get rid of this soap capping, this PVP capping. That's why we do a pretreatment before catalytic reactions. So I will show you a couple of case study what we did. So let me show you how can we, what we can do. Usually what I will show here is mostly gonna be based on carbon dioxide reduction. Carbon dioxide is a big problem in air quality, and also we believe that carbon dioxide is a nice fuel. We just have to somehow find a way to use it again. So one reaction, what I will show you, carbon dioxide hydrogenation. We usually here use atmospheric pressure, so the main product gonna be carbon monoxide and methane, but at high pressure you can come up with methanol. And also there's gonna be another reaction, ethanol decomposition. Also, ethanol, if you nicely can decompose ethanol, you can produce hydrogen from bioethanol. So these are usually the most two reactions, but there are going to be different others too. So anyway, here, this is actually my favorite study. What we did is that, so what you can see here, we bought it from Merck. It's cobalt oxide. Okay, we put it platinum nanoparticles on there with the regular wet impregnation method, as industry does. This is for reference state. So this is an SBA15. So that's an inert silica support, supported a small 5 nanometers platinum nanoparticles on the surface. And this is a cobalt oxide. However, this is our mesoporous cobalt oxide with 5 nanometer platinum nanoparticles on the surface. Okay. And then what you can see, I'm sorry, this is in Hungarian, but I'm telling you. So this is the temperature, and this is the methane, the formation rate of the methane. So the blue one shows the platinum SBA15. Yeah, that's an inert silica. It's not working, the support. The black one shows the commercial catalyst. Okay, so it started to produce some methane, and then it's starting to die. Okay, and then here the red one shows our design catalyst, which is active even at 300 C, and the activity is much higher than the commercial catalyst, just because we designed this catalyst with the size of the particles and using this special support. And not just the activity was higher, but also the selectivity was better for methane. So you can see the pure platinum on the SBA15 produced only CO. The impregnated, so the commercial catalyst, produced a lot of methane, how about 20% of CO, and then here you could produce 100% of methane from the CO2, which can be burned again and then gain some energy. The other one is we also do tailoring this catalyst in photoelectrochemistry. And then here, with a lot of work, we try different sizes of particles with different loading. And then we loaded these nanoparticles on this mesoporous nickel oxide surface. And then what we found that just the regular, and then we produced hydrogen from water. So that was the main step, using photoelectrochemistry. So you use electrochemistry plus you shine light on the surface, and then together with this technique, you can produce some photocurrent, which is also meaning that you're producing hydrogen from water. So this is the regular cathode technique. This is the photocurrent what you get. This is the anodized nickel oxide. So the special mesoporous nickel oxide was almost 5 or 10 times better. And then when we used our platinum nanoparticles, so the best size platinum nanoparticles, we can use almost the 20-fold increase compared to the regular electrode system. Also, we use this system for UV light sensors. So this is a platinum nickel oxide system. And then so here, these are the mesoporous nickel oxide, and then these small particles on the platinum. We put it 2 nanometer platinum 6, and also we put it 8 nanometer platinum on the surface, and then we check how they acting as UV light sensors. And then what we found here is that so this is the pure mesoporous nickel oxide. However, if we used 1.6 nanometer particles, the photo response was almost 3 times higher. Okay, so here in this case, we find that if we use the small nanoparticles, they will help us a lot. And in your mind, you can say that, oh, sure, the smaller the particles, the higher the surface, and that's the best. But it's not always the case, because you always have to be careful that maybe the surface is not enough, that a big molecule can attach to that, or the surface charge will kill the reaction, or there are not enough, for example, 111 Miller indices on the surface, which is running the reaction. So anyway, but here that's really true that the smaller the particle, the higher the photo response. Here we went to the liquid phase for a paper, for a reaction, and then we did hydrosylation reaction over size control platinum nanoparticles. And then this is a very famous reaction in pharmacy and rubbers. I'm sorry, I'm not an organic chemist, so I don't know too much about this deeply. I know that this reaction has a lot of root. And then usually, so you use phenylacetylene and triethylene, and then from these two guys, you want to get this hydrosylation, this cis-beta product, and then the alpha product. But also there are a lot of size product. What can happen? You want to avoid them. You want to have these main products. So we used our size control nanoparticles, and then what we found is the 8 nanometer particles was almost 5 times better than the 1.6 nanometer particles. So here the bigger particle was more active, and also selectivity-wise, you can see that. So the blue and the orange shows the alpha and the beta product. However, the gray shows the psi products. And then you see the smaller the particle, the more psi product we generate. However, if we use higher particle size or bigger particle size, the psi products concentration will be lower, and then we will get more alpha and beta products. Just a couple of studies I showed you in the beginning that we use this alloy platinum cobalt nanoparticles, and then it's always a question that how can I be sure that we have an alloy and they are not just separate platinum cobalt nanoparticles? So here's the proof. Once the XRD shows that they are in the platinum, so the XRD shows that they only just one FCC crystal structure of the platinum, and also ED shows that here are these two particles. So this is the TM images of the particles, and this is from one particle. You can see this is also TM image, and then you can see that it's full of with cobalt and platinum, so we can be sure that this particle is an alloy. And then we use them in CO2 hydrogenation, and what we got is that compared to the pure platinum nanoparticle, our activity was almost 2 times higher if we use the platinum cobalt 50-50 ratio. So we can also, so what we did is that we decreased the expensive platinum concentration and used, a way cheaper cobalt in there, and also the activity was way higher. And then I'm gonna talk here about some how can we design interfaces, and I will go into using more in this transient metal oxide supports. And then, so this is the reaction, what I told you, the ethanol decomposition. This is going in the gas phase, about 200 to 400 Celsius degree. And then you can see through this reaction, first there's a dehydrogenation. You get acetaldehyde, you want this hydrogen, and then this can form to CO and methane. So what we did, we used the tungsten oxide nanowires, and also add small and bigger nanoparticles on the surface. And then maybe this is I just want to show here two messages. One, so this is the inert SBA15 support, and this is our special tungsten oxide support. So first of all, in activity, you can see that if we use the tungsten oxide, so the turnover frequency is here about 0.06, about here is 0.15. So it's almost 2 or 3 times higher, the activity, compared to this one. The other one, the size effect. Here, the smaller particles has bigger size effect. However, in the tungsten oxide, there are not a big size effect. However, we still can say the smaller particles has better activity. And the other one is the cell activity. So here, if we use just the regular support, we have methane, acetaldehyde, and CO as a product. However, if we use tungsten oxide, I can tell you that we have more products and more complicated reactions. So it was really interesting that we could form acetone, from this reaction, which was really cool stuff. Also, we tried, to put these platinum nanoparticles on cobalt on different mesoporous oxide supports. You can see here cobalt, cerium, manganese, nickel oxide, and so on. And then what we found here is that the nickel oxide and also the cobalt oxide supported particles was the best in CO2 hydrogenation and CO2 activation. Okay. And also methane selectivity-wise, this catalyst was the best. And also we tried this reaction in CO2 methanation. So this is a bit different reaction, but it's also an important one. I don't want to go to details, but if you have questions, just let me know. And we still find that nickel oxide was really, really useful. And then the products from here is the syngas, hydrogen and CO, and it's really hard to take the ratio around 1. But with the pure nickel oxide and platinum nickel oxide, we can use, we could reach this ratio of 1, which is really good. And also we had this question that, hey, so this is the pure nickel oxide and this is the platinum nickel oxide. And wow, the nickel oxide is better alone than the platinum. And then we found, that we can produce noble metal-free catalysts. Also, we don't need for the platinum sometimes, because if we can do a nice reduction of the nickel oxide, there's going to be a nice interfacial part of nickel oxide, and that's going to be responsible for the reaction. But I will show you this in details later. Also, we had a study about, always everybody, and also we used silica as an inert support. We always say that, okay, the reference state has to be nanoparticles on the silica support because silica is inert. But are they really inert? That was our question. So we had 3 different silica support, MCF17, SBA15, and it's a silica foam. And we found, XRD, BT-wise, and Raman, a lot of structural stuff was the same. The surface acidity and so on. So a lot of structure showed that they are kind of pretty the same. So what's going on? And so we expected that if we use them as a support, we will get the same activity in ethanol decomposition. However, we found that there were differences in catalytic activity and also catalytic cell activity. Okay. And then what we did, so we were kind of the first who used the small angle X-ray scattering to understand the surface of the silicas. And then what we found that we have different meso and surface fine structure. So for example, while the MCF17 has a fine surface, like a flat board, the SBA15 has a more rocky surface. So these rocks and hills about 1 to 2 nanometer big. So it's kind of a nano, nano rocks and nano hills. And the silica foam is kind of, like a mud. So the structure is so amorph at the surface that it's a different structure. So believe that differences is coming from this. So when you put a platinum nanoparticles on these different surfaces, however they are inert, in this interface they are not inert, and then we will have different interfaces which led to the different catalytic activity and cell activity. And now I will show you 2 case studies about how can we understand this reaction on the molecular level with in situ techniques, and then why is that good. So one study was about the platinum nanoparticles on nickel oxide surfaces. And, what we did here, I showed you that this platinum nickel oxide system was really interesting, and the nickel oxide was really active if we use, them in a right way. And then what we have here is the mesoporous nickel oxide, and we added platinum nanoparticles on the surface in 1 and 5% concentration. And then for reference state, we use 1% and 5% of platinum nanoparticles on the silica support, which is kind of inert, but now we saw that not that inert, but it's more inert than a nickel oxide surface. So in CO2 hydrogenation, we found that the reference state wasn't active. It's okay. The nickel oxide was really active. And then if we used small amount of platinum, it was a bit better. But if we used a lot of platinum, it was just killing the reaction. And also we found selectivity-wise the same. If we have a small amount of extra platinum, it helps for the methane selectivity. But if there are too much platinum, it just decreases the methane selectivity. So what we did on the reaction condition, with ambient pressure XPS, we checked our structure, and then what we found here, it was really interesting. What we found, if you have a pure nickel oxide on the surface, if you use nickel oxide, so after reduction, you will have a lot of nickel on the surface. And under reaction condition, there are going to be a small oxidation of the surface, and then you will produce more nickel oxide on the surface, so the metallic nickel started to oxidize under reaction condition. However, if there is a small amount of platinum on the surface, it's going to be vice versa. So the platinum helps for the reduction of the surface, and there are going to be more nickel on the surface. So maybe this graph shows us that. So we can say that the surface is about 70% metallic nickel, and then there are small platinum nanoparticles on the surface. But slowly, if the platinum is on the surface, on the reaction condition, it's kind of pulling out the oxygen from the surface, and then started to reduce or help the reduction of the surface. So this may be one option why, the small amount of platinum can help the catalytic reaction. The other stuff is the operando IR spectroscopy. So with here on the reaction condition, we can say who are the intermediates of the surface. And then I don't want to go too much into details. I just want to say that, so there are 2 reaction routes. It can be this perturbated CO or the formiate route. And then we could see, how much are these guys on the surface on the reaction condition on the different catalytic, different catalysts. And then we found if we have this 1% of platinum nickel oxide, there is a strong perturbated CO weight. So we believe that maybe, this is responsible for the catalytic activity. So here, I know this is this is the CO2 hydrogenation reaction pathway step by steps. So here and then, so this is the formiate pathway, the direct CO bond cleavage pathway, and so on, the water gas shift pathway. And then, so now from this IR spectroscopic results, we knew that we are on this way. So we are going through this path. And then we also know that we're producing a lot of methane. So from this guy, we produced a lot of methane. So now we know that, okay, so how can we ask this guy that, hey, please, from this step, don't go this way, but please go this way. Okay, so this is kind of the basic of this designing. And then this is how, so now we're staying here with this catalyst, but now this gives us idea how to design our next catalyst to be able to produce methanol maybe under lower pressures. Okay. The other study was this about cobalt manganese oxide nanostructures based on spinel structures. So what we have here is that we have a cobalt oxide spinel, and then we started to produce mixed spinel with manganese, nickel and iron. And then we started to add more and more manganese, so from 0.1% to 0.4, sorry, not percentage, but 0.1, 2.9 ratio and more until reaching the 1:2 ratio of manganese cobalt oxide or nickel cobalt oxide or iron cobalt oxide. From the Raman spectroscopy and XRD, we could see that we have different spinel structures. And then what we found in catalytic activity, that this catalyst in CO2 hydrogenation was really active and really highly active. But the other, what was more interesting, that so usually in this reaction you have to know that at lower temperature it's kind of easier to produce methane, you know. So this is showing that if you see a lot of green stuff, that means you are producing a lot of methane. If you see the red stuff, that's producing carbon monoxide. Okay, at lower temperature we're producing methane, that's also really good, you know, we want to do that. But if we're going to higher temperature, just due to the thermodynamics, the CO gonna be, you know, the main product. However, what we found is that if we use this manganese cobalt structure 1:2 ratio, we still can produce 50% of methane even at really high temperature. And then we checked the literature, and we were one of the, you know, kind of the best who could produce this high methane selectivity. And then we wanted to know what's going on, why this is happened, what happened. So what we used here is this is a electron diffraction technique. So this is an ex situ method, but we checked the pristine sample of this manganese cobalt oxide, the pre-treated sample, so before catalytic reaction and after CO2 hydrogenation. And then we could see from the electron diffraction technique that first we had this spinel structure, but after the pre-treatment we had kind of a mixed oxide structure. But after the CO2 hydrogenation, we have a cobalt manganese oxide structure formed. And then also we checked this with you know, the energy dispersive spectroscopy in the TM, and then we could find that, so how the structure changes during the reaction. So first of all, we had this spinel structure, and then there's, you know, there formed smaller islands of oxides, and then finally we will have big manganese oxide chunks, you know, which was supported, I mean, on the surface there with cobalt nanoparticles. And also the ambient pressure XPS showed us that during the reaction, the cobalt on the surface, the cobalt 2+ is going to cobalt 0. However, the manganese 2+ stays manganese 2+. And then we believe that there is an interface synergetics of this cobalt manganese oxide, and that can be one reason why we have this high methane selectivity. And also we could check, you know, the IR spectroscopy, and now we found that instead of going through that perturbated CO pathway, what we saw before, we could go through the formate pathway in this reaction. So we believe that we have this high activity and high methane selectivity at high temperature, which is coming through the special cobalt manganese oxide interface, which is responsible for the formate route towards the methane selectivity. Okay, so this is the way how we can understand reactions on the molecular level. And then I show you a couple of scaling up tests and pilot tests. So here, what we did is that, so one option was that we cannot always use this design catalyst. So, you know, here we try to come up with ideas which is cheap. So that's why we use zeolites from a special mine in Hungary, and then it's way cheaper than the laboratory, but we want to scale up our systems, and then we try to use catalyst. In exhaust system they usually use platinum and iridium, but we want to use noble metal free catalyst. So our idea was to produce a cheap industrial catalyst for exhaust systems. Now it's a bigger problem also here in Hungary, that you have a lawnmower or you have small engines like this generator, and there is no catalyst or converter on it. So now we try to work on these catalytic converters for these systems, and then to reduce CO and nitrogen oxide and total hydrocarbon and so on. So what we did, so you had to go to scale your system. So what I showed you before, we just used powders, but now we had to make small forms of Rushig rings and so on. So we produced forms. We had the catalyst on the surface, and then here what you see, this is this power engine, and then we designed this catalytic system on the top of this guy, and then here you can see as we add these small forms, the catalyst into this catalytic guy. This exhaust system. And then what we did, here the exhaust gas is coming out, so we measured a different power of the engine, the pressure, temperature, CO, methane, NOx, and so on. So anyway, we try to do real measurements. And then here, this is the reference state, and this is our zero-type exhaust system. What you can see here is that in the case of the nitrogen oxide, so this was the basic results without catalyst, and with our catalyst you can see this was really, really small compared to this one. We wasn't too good in CO, I don't know why, but we still have to work on it, but we are really happy that we could reduce NOx easily without using precious metals. And also here so this is a big engine. This is a 10-liter diesel engine in Budapest. So this is the engine of autobus, which was used in Budapest for commutation. And then so this is a 10-liter diesel engine, and what you can see here, so the exhaust system is coming out here, and then at the end of the exhaust system we added so here is our catalyst bed, and there is 40 liters of this catalyst guy inside. And then the problem was it was too far away, so it wasn't the temperature was a bit low for the catalytic converter here, but we tried. And then what we found here, so I'm sorry this is Hungarian, but so here we couldn't achieve good results with NOx. So the blue one is the basic one, and these are with the catalytic converter, the green one. So in the NOx wise, we wasn't too good. However, in the CO wise, we could reduce the CO pretty much. So this is a California test. So this is a standard test what we have to do, and these are different powers what is put it on the engine. And then anyway, what you have to see here is that there is a big reduction of CO, and there is a big reduction of total hydrocarbons what we could reach. Okay. And then also now we're not just working on exhaust systems, but also we want to go and scale up our CO2 hydrogenation reactor. That we are producing a lot of CO2 and we have to do something about it. And then we have hydrogen from water electrolysis, or maybe from ethanol we can get hydrogen. And also this is not new. So there are a couple of plants in the world. For example, the Georgiola plant in Iceland, it can produce 4,000 tons of methanol per year, and they are using this kind of catalyst. So there are more effort to do the scaling up, and we started to work on that also. So usually, the test, we use 100 milligram of catalyst with a flow rate of 30 to 50 milliliters. And now we're doing our scaling up test. We're using a Phoenix reactor, and then we have to change the system, and then we have to work on it. We're building a new system for the scaling up, and now we are here somewhere using 1 or 2 grams of catalyst with a bit higher flow rate. And then our idea, and hopefully in the close future we can go up to 50 or 100 gram catalyst with a way higher flow rate. So So, but this is also different. So understanding something in the molecular level is different, and also the scale up is a different and needing a different way of science. And then we don't know. We always have problems. If you scale up, you think, oh, I just do it in double, but it's not that easy. So the scaling up is a big challenge. So we are working on that. So I think with this, I just finish my talk, and I want to thank you very much for your attention, and thank you. I really appreciate that I could share my research. Thank you very much.
Hello. Hello.
Hello.
Dr. Sapai, there are some questions.
Okay.
One question, how to get the plot of binding energy and bind gap? Can you throw light on this?
How can I get about the binding energy?
And bind gap. And bind gap.
Oh, the band gap. Yeah, for the small particles. Or also for the interface. I'm not exactly on this. So I'm not a physicist, so I cannot, but I can give you, if you are interested in it, just write me an email about it, and I can send you papers, a lot of papers about, calculating, the band gap of these particles, and then the how the interfacial energies are going. I have a couple of nice paper about it.
Okay, sir, there is one more question.
Mm-hmm.
What is effect of adding too much catalyst in any reaction? What is effect of adding too much catalyst in any reaction?
Mm-hmm. Yeah, you think, I think now the question is about if I add more catalyst on the support. So usually it's good, because you have more platinum on the system, you will have higher catalytic activity. But sometimes you will reach an end because of too much conversion, so there can be diffusion limitation, and also it's expensive. Platinum is expensive, so you want to go into lower, you want to use as low platinum as you can, that's the main stuff. But otherwise, so basically the more platinum will produce more activity. However, you saw in my presentation, we use more platinum, and that was just kill the reaction, because in the nickel oxide, because it started to reduce the nickel, and then there were too much over reduced nickel, so there wasn't remained nickel oxide, and then that killed the reaction. So it killed the interface. Yeah, thank you for the question.
Okay, sir, there is one more question. How nanomaterials can be used targeted drug delivery at the specific disease site? How nanomaterials can be used targeted drug delivery at the specific disease site?
Yeah, this is also kind of a biology question. We're teaching it. So what I can tell you is that, so nowadays, what they can do is that what is good in these nanoparticles, that you can add any kind of ligands on the surface, and then you can add this, and to these ligands you can connect your drugs. And then, for example, you have a magnetic nanoparticles. You drink the drug, maybe a chemotherapy, and then for example, there is the cancer maybe in your elbow, or I'm just saying something, and then you put a magnet here, so all the magnetic nanoparticles will come here and then release the drugs only here. So you can use targeted drug delivery. Also, another option is using the heat. So sometimes with these nanoparticles and connecting the drugs to the nanoparticles can be sensitive for the heat. So they are just bringing the drug everywhere, and they cannot, do the effect. However, for example, there is some problem here. You start heating this part, and then the drug come here with the nanoparticles will release the drugs, and the drugs can act as a drug, and then you can use its benefits. Okay.
Okay, sir, thank you so much.
Thank you very much.
Sheena ma'am. Okay. Sheena ma'am.
Yes, ma'am. Am I audible now?
Okay. Yes,
Yeah, we
yes.
can
Hello,
hear you.
am I audible now, ma'am?
Yes, ma'am.
Yes, we
You are
can hear you.
audible.
Okay, thank you so much. Yeah. Okay, thank you so much. Let me begin by professing the vote of thanks to the first speaker. Thank you, Dr. Sunita Rattan ma'am, for all the insightful talk that you have given on today's topic, and it was very much relevant. And the talk focused on different methods of dispersing nanoparticles in polymer matrix with emphasis on swift ion, which have vast potential in the field of modification of materials by extremely large energy transfer through electronic excitations. You very accurately threw light on addressing challenges associated with the dispersion of NCPs within the polymer matrix for their enhanced performance towards the various applications. I thank you very much, ma'am, for your valuable time and for your thoughts, ma'am. Let me move on to the second speaker. Thank you so much, Dr. Andrea Sapai, for the enlightened talk on nano catalysis by designs from the molecular level understanding to the scale-up applications. The study was very interesting. The study on the interface and action was really very interesting. And the talk was very informative. And we are very much thankful for the time that you have spared with us. And we are very grateful to you, sir, for all the information that you have shared. Thank you, Dr. Andrea Sapai. And overall, I think both the sessions must have really benefited the participants, and they must have a fair idea about both the topics. Thank you, both the speakers, with a lot of respect, and we look forward for a long association with you. Thank you so much, sir.
Thank you very much. I appreciate it. It was good to be here. Thank you.
Okay, thank you so much, sir.
Thank you, sir.
Sunita ma'am also, thank you so much. So the next session, session third, we will start at 4 o'clock. So all the speakers are also requested to join with us. So Sheena ma'am, at 4 o'clock, we will start with our next session. So we already circulated attendance on YouTube link. So the second session attendance is also covered. Yes, yes, ma'am.
Yeah, so we have to just one information we have. Attendance is mandatory. The feedback will be given tomorrow. So both the sessions, there will be 2 attendance which will be circulated today. And I want all of you to fill up the attendance without fail. So see you again at 4 o'clock sharp. Thank you so much for being here. Thank you, the speakers, once again. Thank you so much. to the afternoon session of International Seminar on Emerging Technologies of Nanosciences, Environment and Energy COVID-19 Restriction. The next speak is going to be about global refining industry, emergence, and some interesting facts. This session will be hosted by Mr. Shinoj Bhaskar. He has overall experience of 20 years in operation, process engineering, and management, currently working with the Aspen Tech as Director Product Management for the most recognized brand named PIMS, that is Process Industry Modeling System, and the development product AUP, that is Aspen Unified for Planning. This involves managing current product transitions, the tools to meet the next generation requirement, which will replace the current version of PIMS. Meeting and managing the expectations of the current customers, that is 470 plus sites, managing and guiding the team of R&D development teams for successful futuristic product on time and budget, catering strategies for successful transition and creating the roadmap with marketing for the same area role, planning and optimization. Using Aspen PIMS and Spiral Plan for refinery includes responsibility for 3 months rolling plan, monitoring, coordination, and month optimization, model maintenance, updates and version updates, evaluation, implementation of alternative planning, linear programming tool Spiral Plan, evaluation of kinetic model for updating the base delta vectors, planning for crude procurement and economics, margin variance analysis versus plan and management reports for planning and scheduling team, retro analysis for the given months, long-term crude procurement strategy, configuration study for refinery expansion. And the list is endless. Without wasting much of your time, I welcome sir to this session, and I hand over my mic to you, sir. With great respect, I welcome you, sir.
Thank you, Sheena, madam. Am I audible, loud and clear?
Yes, yes, you are loud and clear.
Okay. I thank KCC College for this opportunity, and I'm really excited to be here and present what is happening around the world in terms of refining and other prospects. And I welcome all the participants also. Really excited to be amongst the young engineering graduates who have joined online. So a good welcome to you. I think it's a great initiative on the part of KCC College to organize such an event and to use best of the time that you have today. So with that, I'm going to take you through a small journey. So let me share my screen and let me know if you are able to see it. Give me a moment. So let me know when you're able to see my screen. Okay, great. So the whole idea today here is that this is what I'll be taking you through. So I think I wanted to make the session a bit interesting in terms of what is, I would want to start with something very basic and want to bring the audience on par with just, let's say, what is crude oil refining, right? Everybody has certain idea. I just want to set the baseline right in terms of what it means. And since it's a very young audience, I would like to also get into some technical aspects which you might find it interesting. Yes, we do all study during all of the college days and we hear about it. So I'll be just delving into some of the basics of what is petrol, what is diesel, what is kerosene, and what makes it the product what it is, right? And since we are talking about a refining sector, right, and I think there would be some of them would be chemical engineers like I am. So I would want to take you through some of the interesting aspects that you study today and how that gets translated on the industrial platform. All right. So that is where the role of a chemical engineer is to take something which is in a design and a concept and convert it actual scalable operation for the big time usage, right? So it's a mix of chemical, electrical, mechanical, electrical, and other basic engineering trades which are there. And it's a chemical engineer who does all the conversion into for the product to be used, right? And once we have studied gone through the basic concepts, right? The whole idea here is that is there something that we can look at and see the history of oil, correct? When you are in the refining sector, right? There's a very interesting story, which is of the Standard Oil. It is before our generations that Standard Oil as a oil super major arose in the late 1800s, and how there was a big battle, and how all the major companies that we see today have emerged from that, right? So that should give us the story of the Seven Sisters and why the Seven Sisters. If you are interested, just go and type in the Google the Seven Sisters story. You will come up with the entire history of the refining oil, and I would recommend there is an video of the Seven Sisters. I think it is a documentary by Al Jazeera channel, and if you watch through it, it's each video is around 45 minutes to an hour, and there are 4 or 5 part series. It will give you what the world is today, including the turmoil which is happening in the world, not related to COVID but related to other geopolitical scenarios, and what is the role of oil in all of these, right? So that is a very high level story of what everybody who is interested in this should come up and read and watch about it, right? And then we'll get into, okay, we are in a world shifting paradigm, which is called COVID now. And COVID has impacted the industry in an unprecedented manner. When I say in an unprecedented manner, you, me, everybody is impacted. The photo which was circulated of mine, I didn't have a beard, so you can see the impact on me. Now I'm sitting at home in last 3 months, and I'm working from home. I'm interacting the world over. It has changed completely my life in terms of how I interact with people, how I interact with customers. So that has got a major implication on the refining and the operations and the fuel market. It has impacted everybody, but the topic of interest today is how it has impacted us, and especially the Indian refiners too, right? We'll go through certain numbers in terms of how the Indian refineries have been coping up, any public sector, any private sector refinery, right? That how it has been coping up, and more importantly, how they have managed the situations operationally, and how they have managed the situations in terms of margin wise. I'll also take you through a bit global scenario, how the oil market is changing, right? Because if you, just to give you some facts about what has happened in the COVID situation, right? The location where I am, it is in US, right? And here the major airlines, if you talk about, are the United and the Delta. They are the largest carriers in this region. So just to give you the impact, that at the peak of the COVID situation that was being faced here, United, the largest airline, amongst the largest airline, was just operating at 3% capacity. So just look at the impact of that. What does that 3% capacity mean? It is not just that the planes are not flying. It just means that the airport and its related infrastructure is not no longer useful. Layoffs in that region. What it means is that the entire airport maintenance staff no longer required. The entire infrastructure which is just inside the airport, of the shopping and the shops, everything no longer required. So airport security completely not required to the scale it was. So just I gave you a small example of an ecosystem where just an aircraft, which we typically use, I don't know, once, twice, maybe 10, 15, 80 times a year, right? That has impacted everybody. Just to give you another aspect of that, is how the airline industry is being saved by government, right? So just again, certain numbers to make the conversation a bit interesting is United is having bailout packages. Typically, we hear bailout packages of a few 100,000 crores and this and this. But what is happening, just to give you the publicly available numbers for United, they are being given a package of 5 billion US dollars or 9 billion US dollars as a bailout package, and that too just for the 8 or 9 months. So all this is to drive the gravity of the situation to the audience in terms of what is the impact that it is causing. And then what we'll do is we will see that, okay, this is the consumer end, correct? What I talked about, correct? The people who have refineries, they are producing, and there is a consumer market who is taking that product and doing it. But what is the impact on the oil producing nations, right? So you might hear that, oh, last 14 days, I was just reading paper yesterday or day before yesterday, and there was a lot of hoopla about the prices in the last 14 days have been going up of the crude oil, or even for the refined products, right? So how does everything play into that, and how are the oil producing nations surviving in that? So we'll get into that aspect too, and after that we'll get into, if you have got any questions and answers, we'll get into that, and I'll try to answer it to my best of ability, right? I might not know everything, as the situation might arise, but I will try to help you as much as possible if there are any questions. Hope it makes sense. Sheena madam.
Yes, sir. It does make sense. Please go
Sure.
ahead.
And if there are any questions, do let me know, right? I want to make it as interactive as possible. If there are questions, do stop me, right? If there are certain things which does not make sense to you, do stop me. Let's make it a bit interactive. And if you think that I can add certain flavor to them, or if I'm presenting certain facts which you might think, oh, that's interesting, I do not agree to that, yes, it can be a debate too, right? So with that, let me jump over to some of the slides, right? So before getting into the detail aspects, right, you can see very quickly from very basic, we'll be getting into from the textbooks, which is these slides, into pretty high level very quickly. So do let me know. I just wanted to be aware of the audience and let them, I wanted to create awareness rather than giving them anything in terms of very specific things. So most of the slides and most of the information is available in public, and I've just collated some of the information, and you can see every slide will have the source of it. So if you want to go ahead, if you find something interesting, you can go back to that and get more detailed information, right? So I just wanted to first touch upon what is crude oil refining, correct? And it's a very simple fact. Right. No, this has been there since the time oil was discovered in the basic form, but over the period, certain improvements have come through, and people have realized that it has got, once distilled, it has got very distinct properties which they can utilize. So the basic process of refining goes as just you heat up the crude oil, put it in a fractionation distiller. It is nothing but a big column, or it can also be called as a pipe still with various draws out of it. And those produce the major products that we think about, right? And this is a very simplistic form of thinking that what is a refinery, right? And when you look at that, what does refining entail? When you distill something, you bring out different level of boiling points which are there. So if you look at in that aspect, so when you are taking the gas out from the oil wells or from whatever be the source. Fracking is another source which has caught up these days very heavily, right? So all you do is you get a lot of gas during that and you burn it, right? And you used to burn it till a few years, or I should not say decades, but till few years ago that was considered a total waste. But now there are technologies even for the gases which are coming out during the oil production that is to be utilized, because again environmental concerns are the biggest things that are there on the planet, and all of us face the consequence of the environmental implication of that. So there are technologies which help you recover the gases which come out, right, which is known as associated gas, or if you're in the natural gas business or other gases, you try to utilize every bit of it. And there is an interesting slide, and but in an Indian refinery scenario which will help you understand that. Correct. So this distillation process, correct, based on temperatures, these temperatures are in degree Fahrenheit, obviously, because in this region when I do Google search it comes up in degree Fahrenheit, but the part of the world where I'm giving the most common units are a degree centigrade. So bear with me, it's a simple conversion if you have to do, but these temperatures are what defines the product. And just to let you see that there are gases which come out. Gasoline has got a temperature range from 65 to 185. Naphtha, again, typically you don't hear naphtha because naphtha has got two components. Either it gets blended into gasoline, or it gets, depending on its properties, into petrochemical sector. And India is one of the largest consumers for the petrochemical and this other sectors, but the price of the naphtha is determined based on the Japan's, Korea and other regions where it is much more in demand, right? Kerosene is the most interesting aspect today the refiners are facing as a challenge. I say challenge because what comes out as a kerosene, in typically in India we call kerosene is what comes to my mind as the public distribution system and the kerosene which is associated. But this is also has got a characteristic which is used in the aircraft fuel, which is known as a jet fuel, right? So that is where jet comes in. Diesel, we all know it is the main public transport. Everything is done on the diesel, be the trucks, cars, buses, right? And this is where this was sustaining the COVID for a few of the for some time, but we'll come into that also how it was helping in the early stages of COVID, but now it is again proving to be a problem. And this is fuel oil. Fuel oil comes out from the bottom, last second product, and fuel oil is another major thing which the world has seen as a spec change, which has caused a lot of margin issues for most of the refineries, and we'll come to that why it is, right? And the last part is residue, which you cannot distill or crack, which is you can say that it comes out as a tar, and think about it as an application in terms of where it will go. So we talked about all of these, and here again this is a slide which you can search in the Google and get it, right? You have got typical products which are coming out, right? So now you might ask me that, okay, you talked about residue, you're talking about tar, but now I see that you are also producing gasoline, diesel, fuel oil and lube stocks out of that, right? So in between, this is the column, correct, which is denoting the typical unit operations where most of the chemical engineers would be interested, and that would be their one of the subjects for studying, right? So this unit operation is what purifies these products which are coming out of the pipe distiller and converts it into a final usable product. right? So the gasoline which comes out here, correct, it might be very high in sulfur, right? And in case you have not experienced what a high sulfur means, if you have got burning eyes when you're in traffic, right, or if you see a different smell which makes you suffocated, right, those are the things which you will see from an unrefined product, correct? The refined products are environmentally safe, right? They all the sulfur and other impurities which cause the SOx, NOx and all emissions, correct, they are controlled. And all of the products have got certain specifications which are set by the government and by the environmental agencies, so that they reduce the amount of pollution. I would not say they remove, they reduce the amount of pollution and the impact on the humans and the environment, right? So that is where all these secondary units come in. So in refining parlance, this is a primary unit and these are the secondary units, right? And once processed through secondary units, they get into the final shape, where if you are going to an petrol pump and say that, oh, I want a gasoline which has got high octane, right? What does a high octane do? It provides more power to the engine, right? So those kind of things come. Same goes for the cetane. So each one has got its own characteristic that you might want to adhere to make you stand out, right? HPCL is pure for sure, or BPCL. Each one has got its own branding of the product, in which it is not just the product, but there are certain additives which are added to make the things much more useful to the user. And if the users can find the difference, they will stick to it. So you need to have a differentiator in your products also, because this market is highly competitive, and each metric in terms of selling creates the margin for the user, right? So we have talked about. Just to recap, uh, distillation is nothing, crude oil taking in, distilling it to different temperatures. Those different temperatures come out and they are pushed through secondary units, and those secondary units are where your final products uh, come out from the refinery, right? So this is all good, but how do we visualize it in terms of um, certain basic things, correct? So all that is fine, but what is crude oil, correct? So crude oil is nothing but a chain of carbon, hydrocarbon, and that is why crude oil is also called as a hydrocarbon, because there is only just hydrogen and carbon associated with it, and there are trace elements of others which we call as impurities, which are typically removed, right? So when we look at the we were discussing here temperatures and others, but those temperatures in terms of the carbon and its chain length is what makes it the unique characteristics that we are talking about, right? We talked about gases. The gases are C1 to C4. That is nothing but a chain of hydrocarbons linked together, carbon and hydrogen linked together. And if the chain goes a bit bigger, it gets into gasoline. It goes into a bit bigger, C6 to 610. Now, this is an interesting space. So when I'm talking about it, all of you might be thinking about a straight chain carbon atoms, right? Which is fine. But if you look at, I told you, naphtha gets into petrochemical, all right? What does petrochemical mean? Petrochemical, if you think about it, any plastic is in petrochemical product, propylene, polypropylene, polyethylene, correct? And there are complex molecules like xylene, toluene, paraxylene. So now if you look at it, right, this C6 to C10 is what creates the aromatic structure also, right? And we will come to why the complex structures also cause certain issues. But this is what makes naphtha a very interesting feedstock for petrochemical, because you get benzene, xylene, toluene, paraxylene, and its derivative also out of this. So there is a whole different set of units which emerge out of this. Then you have got kerosene, we talked about, airlines and jets, right? Then diesel, we talked about, trucks are the major consumers, right? Transportation fuel, lube oil, this is again an interesting aspect, but this is an industry which is being replaced by more synthetic lube oils. Traditionally, it has been driven from the crude oil, and there are certain characteristics in the crudes that you have to make a lube oil. But again, this is now being replaced by synthetic lube oils, and you might see in the advertisements that you might be seeing on the TV also that synthetic lube oil is what is emerging, right? Then we talked about fuel oil, carbon C30 to C40. You can see how each addition is getting making it a larger chain molecule, and the basic science and the chemistry says that as you increase the chain length, the viscosity and the boiling point go up in increase. I'm getting a bit of a feedback. Can you mute? Yeah. Thank you. And fuel oil, we talked about it. And the whole idea here, it is showing that the crude oil gets in, and below it is the paraffin wax and the bitumen, right? And the bitumen is typically what is used for construction of roads and others, right? So this is an column characteristics, and here at least you have got some temperatures which normally people in the region that where we come from in India, you can associate 25 to 400 degrees, right? So this is a typical operating range, right? And one of the things which I talked about the fuel oil and its impact is the IMO, which is the International Maritime Organization, which has dictated from 1st of January 2020, and the fuel oil spec has changed, correct? The ship which used to have 3000 or 4000 ppm of sulfur, now it is being reduced drastically, right? So that has caused a lot of changes in the fuel oil industry, where the shipping fuel oil which is used is typically known as a bunker fuel oil, and that has changed, and which again has impacted COVID a lot, because to remove the sulfur, what you require is something called as a unit operation. So what does unit operation mean? Unit operations, I think most of the people in the audience, if they're chemical engineers, they would understand that unit operations are operations which help you remove certain impurities from the system, right? Each unit operation, it can be a distillation, filtration, extraction, all these are called unit operations. And a refinery is nothing but a combination of unit operations to give you the final product, right? So just imagine, we talked about crude tower, and then if you go through all of these unit operations, it will give you the final products in the tanks, right? So some of the technologies, some of the processes which exist, and each process has got different technology and its associated vendors, but we are not going to get into those details, correct? Because there are certain privacy issues that we might run into. So the distillation, hydrotreating, cracking, reforming, coking, these are the different aspects of taking the crude oil, distilling it, removing the impurities, and converting them into a final product, right? So I would like to take a pause here and see if there are any questions, Sheena Madam, that we would want to address.
Sherry ma'am, do we have a question at this point, ma'am? I think the questions will be posed to you, sir, at the end of the session.
Okay, thank you, ma'am.
Okay, that's how the rule goes.
Okay, sure. That is fine. So this is what we covered in terms of the unit operations, right? So once you have covered the unit operations, we are going to jump quickly into the Seven Sisters story, right? And this is a very complicated slide. I do not expect you to read through it, right? But this is trying to show that everything, any major company that you think about, right? I'm not yet talking about Indian refiners. We will come to, we'll take it as a separate session. But what I wanted to give you is the entire world as a stage is set by just one company, right? And I just wanted to spend a few minutes on this in terms of, this is a very complicated slide, and this is a simplified slide which helps you understand the refining space. So why I took this slide is because for you to understand what is oil industry, right, you have to understand the story of the Seven Sisters, right? And the Seven Sisters are the major oil corporations which are around the world, right? And they have got a participation in majority of the oil production, refining, and the distribution space, right? This statement was more true till a decade or more so ago, but in the last 10 or 20 years, right, more new independent players have come up in this space, but still the entire oil industry is defined by the Seven Sisters and their associated story. So what is Seven Sisters? I told you about the early 1800 late 1800s, right? John D. Rockefeller, he was one of the early guys who saw the potential in oil, and he created a company called Standard Oil, right? And Standard Oil, just to give you an idea, that it was such a big company in when it was formed, that it was dominating the entire industry. I would not say oil industry, it was dominating the entire industry, because energy is something that is required by all, and it became such a big entity that the US government had to intervene, and they had to break it down. So just imagine a company broken down into 34 individual companies, right? And this is a story in 1911. And the names that we see here, right? You see here Chevron, Exxon, BP, Marathon. They are still amongst the largest companies there in the world even today, right? There has been a lot of story which goes behind it, right? What you see today, like take the example of ExxonMobil, they merged in 1999, correct? But they have got a path that you can see. Everybody emerged from Standard Oil, and this is what makes the story of the refining space and the Seven Sisters the most interesting story that you would want to go ahead and read about and get educated, in case you think that oil and gas is something that I would want to spend my career in, right? It's not a very openly discussed story, but it is something that will give you an aspect in terms of give you an aspect of what is the geopolitical angles, how has the history shaped up, or what are the different aspects, why did the crude price go up in 1974, what is the embargo, what happened in Iran and Iraq, how is oil connected to that, what is happening in today in Syria, how is oil connected to that, what is how is Afghanistan connected. So everything that you see today, you can place it for the basic requirement of energy, of having cheap energy as a source, and its political, geopolitical, and its margin impact as one of the root causes, right? So this is just for your knowledge. In case you are interested, you should go ahead and look Google and learn more about it, right? So with that, I would like to jump into what has happened with the COVID. Correct. So again, there is certain impact that I talked about COVID. COVID completely changed the way the world operates. And when I say the world operates, never ever has world come to an standstill. Right. When I say standstill, you have experienced a complete lockdown, um, and complete lockdown means not even a vehicle, not even a cycle on the road, that kind of a scenario, right? And if you look at it now, in terms of its impact, so we are talking about refining space. And in this refining space, the refiners who were there, some of them had to go down even up to 30 to 50% of their capacity, right? And going down a capacity is only one aspect of it. They had to go down because their entire storage tanks for storing the products were full. There was no demand. Nobody was buying any fuel. Nobody was moving any fuel from one location to another unless there are trucks and trains moving. Right? There is no demand for the fuel which is there. This was over complicated by the sudden stoppage of the airlines. Correct. And if you look at it, the slide which I was presenting, right? Uh, Kerosene, right? Kerosene, you cannot produce all these products without producing kerosene. Kerosene is a draw physically in the column. You have to take it out. You can dispose it at a different location, but the most challenge that was faced was by the jet fuel, which was one of the refining products which had to be catered to during this shutdown. So what happened was, this caused a big operational challenge to the refiners. They had to reinvent themselves to find newer dispositions to that jet fuel, which was over there, because nobody imagined a scenario where you would have to operate a refinery where one of the products had completely disappeared, almost disappeared from their landscape, right? And what it has also caused, and I think this is a statement just to give you an aspect, that it is not just the refining, but also its industries which were associated with it, like the trading houses who buy and sell the crude and the products, right? They filed for bankruptcy. And the name I'm taking here is the name that you're seeing here is something which is a very big trading house in Singapore. They had to file for a bankruptcy. So this is something which is not expected to be normalized uh, very easily. And just to give you an aspect on what actually has happened, right? So in this table, right, here you have got all the major refiners that we are talking about, right? And if you see this column, correct, in the 2021, and this is an April data. The May and the June data is not yet out. So this you can get it at ppac.government.in, right, where all these reports are published. You can go and see the impact that what it is causing. So whatever be the target that they had, correct, they were almost 25% lower than the capacity. So this has caused this is the basic root cause effect that we are seeing. Like COVID came in, demand destruction went, refineries were affected. So what does it mean for the refiners in terms of their margins, correct? So when you look at margins, and the definition, the term which is very commonly used is the GRM, which is known as the gross refining margins, and it is given at the bottom. That the definition of it is given at the bottom. It is one of the common measured refinery performance in terms of monetarily. It is measured as a gross refining margin, right? And it is calculated in dollars per barrel, which is giving you the cost of the product minus the cost of the crude, right? And that determines the profitability. It is a very basic way of looking at things, but very well accepted as a performance of the Indian industry, not Indian industry, refining industry. So if you look at IOCL has got 9 refineries, BPCL has got 2 HPCL. So if you look at all these numbers, correct, historically they have been making certain margins, correct. Don't worry about the 9-month performance, right? It is a dollars per barrel. It is month agnostic. So just to give you an impact, some of the refineries, right, some of the bigger ones, I would say, they have had a significant drop in margins, right? And it goes across the board, right? Look at these two columns in 2018, 2019. If one of the refineries like the Mathura one was making $4.65, it is making only $2.5 a barrel today. Some of the refineries in the PPCL, they have also almost half the margin, right? Some of the refineries which are in which have got some other challenges, they are even in the negative domain, right? So the whole point of this slide is that the COVID has impacted not only uh, the basic um, human interaction, it has also affected the industry in a manner which is unprecedented. When I say unprecedented, even I'm not talking here about the producers of the oil and others, right? Because it's a supply chain. If the consumer is not buying, the producer cannot produce. If the producer is not buying it from his source, which are the crude oil producers, then it becomes very challenging in those aspects. So it's a circle where everything went down from producers to the consumers. Everybody right across the channel in the Indian refinery was not just in Indian refinery, the world over, they were affected. But there are some early good signs which is happening around the industry. And I think only the data from China has come out, right? And the data from China is pointing out that the demand recovery is coming in faster than the actual anticipated or the projected demand recovery. And the reason for that is post COVID, people who are coming back, they are not taking public transport, they are taking their own vehicles. And that is causing a demand recovery which was faster than anticipated. So what is happening, what it means is that there is a definite consumer behavior change which is driving certain known principles or the known market assumptions to be reinvented. And this is giving you the same aspect, right? So the entire data is published at a EIA, and if you want to go ahead, and this is a very interesting website where the not just the US, but you will get a certain high level world consumption and other data too. So just to give you an idea, what happened was the graph in here is showing that typically we were around 98 or 100 million barrels uh, a day consumption. So that is the world demand for the crude oil in terms of consumption. All right. So we were net production and consumption always run in a balance, right? There are sometimes when the production goes up, you might hear in that OPEC countries are meeting and they want to curb down the production and all other things that will come to forefront. But at the end of the day, it has to be a net balanced supply and demand situation. Supply and demand here is production and consumption for it to be at a in a healthy place. But what COVID did was that it dropped the consumption drastically. And you see here from 100 million barrels a day, it went down almost to 80 or 82 million barrels a day. So this demand destruction of 20 million barrels a day, it is a huge number. Refineries across were struggling. Some of them brought down, shut down earlier so that they could completely do away with situation. But again, getting the manpower was a challenge in the entire COVID situation. Some of them were lucky. I talked to the refiners around the world. Some of them have been lucky and they have come out of the shutdown without a single COVID impact incident, right? But some of them have reduced the operations. And they are trying to reinvent themselves, and some of them are having certain issues. And when I say issues, some of them are having safety issues associated with it. It is because if everything is stable, everything is known, right? In terms of uncertainty, you go ahead and come out of the operational comfort zone, which has caused some of the issues around the refineries. So that is that topic being separate. Here, this drop down is what is the biggest challenge. And if you see here, there is a line which is depicting this is the current and this is the forecast, correct? So they do expect, and this is a data of May 2020. We are in June, so June data will come out in another few weeks. So this is what is the biggest change that the world has seen. So now we are still overproduced. So what this has caused is, you go a website for tracking the ships, you might see entire ships on the sea are just waiting at the port to be unloaded or to be loaded. All right. So these are the kind of things which are happening. The freight market or the shipping market has completely gone crazy. It went up. If you wanted to transport a VLCC, that means a very large crude carrier, which contains millions of barrels of crude, right? It typically is transported in 50 to 90 cents a barrel, right? That market suddenly shot up because everybody was looking for ships to store crude, right? So that is where the freights went up from 50 cents to $2.70, right? And if you remember my previous slide, right, $2.70 might be the profitability of certain refineries, right? And if you are just paying for transporting that amount of price for a crude, right, it makes the business unsustainable, right? And nobody knew when the demand is going to come back and how longer they will have to store the product. So there was a peak, and now everybody is struggling in terms of, oh, the ships are not moving, the crew is waiting there, and those are very expensive per day demurrage rates that they have to pay. So all of them is now causing a lot of issues. You might have heard some time back that the crude oil also went negative, right? And that was one of the biggest things. That means if you want to buy a crude, somebody would pay you to take the crude away from you. So that was a situation, that was a unique situation which happened in one of the regions in the US. It is called as a Cushing where the benchmark of the crude, which is known as a WTI, that derives its price from that location, and that being a landlocked region, correct? There is the only way of evacuation is the pipelines and the consumers which are associated with. Unlike ports, the port locations is not there. It being a landlocked site, so that caused the inventories to be full. And you can see these are the things which are pointing to the inventories. And once the inventories are full, right, people panicked. Why did people panic? Because again, physical aspect of things are there. We talked about this. Okay, you can store, you can remove, but there are people who could not place the crude physically into those tanks, and you need to have a place by certain date. Those are the contractual and legal terms. Those are there, that you need to have a place to store the crude to buy a crude. So people panicked and they didn't have a place to store the crude. So they said, okay, I will pay you to take the crude away from me. And that is where it hit the historical minus $35.7 a barrel. negative price, right? So that is another interesting aspect that will be talked about. A lot of books will be written about that, and we will hear a lot more in the coming days about the COVID, its impact, and the going of the changing of the production and the consumption, supply demand scenario, how the industry has reinvented itself, how the green energy is now coming into picture, and all those aspects, right? And just to take you to just another aspect of what is happening in this is that as nation, correct, some of the nations just depend upon the price of the crude oil to fund themselves, like, and if you look at the names here, right, they are known as the oil producing nations, correct, and most of their economy is dependent on having a certain price of crude to sustain their entire economy, right? And this slide I'm not going to discuss in detail, but was just to give you an idea of what is the break even price the countries require to sustain, right? And when I say sustain, all the prices here are in dollars per barrel, right? There are prices ranging from $389 a barrel at the highest to a price of $33.07 a barrel, right? So the whole idea here is to give you an aspect that oil industry, and that is that you're seeing today, is undergoing a drastic transformation in terms of how it operates, where it operates. Again, the world is changing in terms of the global economy to a local economy. All that will play into this refining and the other aspects that we are talking about, right? And we'll be, nothing is set in stone yet. Everything is very fluid, and in the coming few months, weeks, and years, probably, we are going to see the impact. And just to give you an impact, the entire capex across, if I want to take an average number, has been cut down by 20 percentage points for the investment which is coming to the oil and gas industry. That is again going to create a lot of unknown impacts in the next few years. So it's not an easy place to be, is what I would say. And with that, I would like to thank you and would like to open up the forum for questions.
Shelly ma'am, are you there?
Yes, ma'am, I am here.
Yeah.
Okay, Bhaskar sir, there are some questions for you. Question
Sure,
number
ma'am.
one, unit operation means, is it the series of processes?
So
Unit operations means, is it the series of processes?
yeah, so it's in chemical engineering term, unit operations. Unit operation can be filtration is a unit operation, right? And when you come to filtration, there are different kind of filters, right? A Niosh filter, a simple decanter can be a filtration process, right? So unit operations typically are defining an operation at a unit level, right? That you can put it that way, right? The idea here was just to give you in terms of how the chemical engineering word translation comes into the refining aspect in the industrial terminology.
Okay, thank you, sir. The next question is, can we expect the price of fuel oils going to increase?
That's a very deep question in terms of fuel oil. I should say that I'm not an expert, but I can tell you what is happening there in the market. The fuel oil um, is very uncertain. It is going a very uncertain time, right? Why? Because of two things. The IMO, which has come in January, correct? It has impacted the fuel oil market in terms that the fuel became very expensive. So most of the refiners were actually looking at the sustaining of the they had invested in upgrading the fuel from 3.5% fuel oil to 0.5% fuel oil, right, or 1% fuel oil. So that investment is under a lot of debate. Second thing which is happening there is people are still using 3.5% fuel oil, sulfur fuel oil, but what they are doing is they are installing scrubbers. That means whatever be the emissions which are coming out, they are installing scrubbers on the ships so that they are able to meet the environmental law. People are reinventing themselves. So it's not an easy question to answer whether the fuel oil prices will go up or come down. What is happening now? People are reinventing themselves, and it is still a fluid. So I do not have a definitive answer whether it will go up or come down. Especially, you should also consider I am not an expert in the price, but this is something that we should keep an eye out.
Okay, sir, there is one more question. Petrochemicals are derived from petroleum?
Yes, most of the I should not say all, but most of the petrochemicals are derived from petroleum products. The only change which has happened in the industry, as I talked about, the associated gas, right, which comes out when you take out the natural gas, right? So there are different kinds of feedstock and technologies which you can combine with to make the petrochemicals, right? Petrochemicals are nothing but C1, C2s and combined together to form polymer and its derivatives. That is the easiest thing that you can look up. That ethylene, it can come from ethane cracking also, right? So the most common source traditionally it has been petroleum products, but now there are emerging alternative sources which are coming up, which are natural gas, which will have ethane or associated cracking, or the associated gas. It can be purified and then used. So all those alternative aspects are coming in.
Okay, sir. There is one more questions we are taking. Is
Sure.
separation is our unit operation? Is separation is our unit operation?
Are separations a unit operation? Yes, they are unit operations. Like if you look at the crude oil, correct? The crude oil, when it is extracted, it is transported, like it gets contaminated. I'm taking a very simple example with water, right? And when you come and place your crude oil into a tank, right? First you're allowed to do is something called as a settling, and it's a very basic experiment that all of us might have done in the childhood or in the school, is that you mix oil and water, shake it and place it. It gets separated because of the density difference, correct? That is a separation process. The secondary level of that separation process is there are dissolved salts in them, correct? That is where you take it into and desalter, and that is where another separation process happens. You apply different voltage across it, and the salts, because of its affinity, are separated from the processes, right? Tertiary level of separation happens in the secondary units, where the catalyst and the chemicals are added, so that catalysts absorb certain kind of impurities. That is another process of separation. So yes, separation is a unit operation, and it has got many flavors which are associated with it.
Hello, Shelly ma'am. Any further questions? Hello? Deepak sir? Deepak sir? Omkar sir?
I think, ma'am, no questions there.
No questions. Shall I move on with the vote of thanks?
Yes.
So thank you, Mr. Shinoj Bhaskar. It was a wonderful talk about global refining industry emergence and some interesting facts. Sir, you guided us through some engrossing aspects about how did oil industry shape up to what it is today, what happened in the last few months, and how this would affect all of us in the next coming months and years. A very big thank you to you, and thank you once again for your time and for a very engrossing talk. Thank you very much, sir.
Thank you, Sheena ma'am. Thank you, Shari ma'am.
Yeah.
Thanks, KC College, for giving me this opportunity. Hope you enjoyed the presentation. Thank you.
Yes, thank you so much, sir. And all the participants, I have a request that we have already floated the attendance. 2 attendance are mandatory, and tomorrow we will be meeting again at the time prescribed to you.